We request everyone to please settle down. We'll be starting in a minute.
Ladies and gentlemen, distinguished guests, and fellow science enthusiasts, welcome to our exciting particle physics conclave. Our theme for this year is Bridging the Gap, particle physics and its relevance in our everyday lives.
Today, we embark on a journey to explore the fascinating world of particle physics and its profound impact on our understanding of the cosmos. Without further ado, let's begin this enthralling day of discovery.
At Shiv Nadar School, we place a strong emphasis on mindfulness, which is why I would like to welcome Ms. Akanksha Mishra, our middle school counselor, to guide us through a mindfulness practice.
Good morning, everyone. Like we said, we believe that mindfulness sets the tone of the day and lets us look within, check in with ourselves. So let's begin the day with just that. Gently close your eyes and focus on your breath. Breathe in and breathe out. Don't try to change anything about it. If you are standing, you can go ahead and do this practice while standing. Find a moment to check in with yourself. As you're breathing in and out, don't try to stop any of the thoughts that come into your mind. Let them come in with the inhale and let the thought go with the exhale. Let your breath follow the natural rhythm of your body. If there are sounds that are coming to you right now, let them come to you. Take a few deep breaths. And as we focus on our breath, set the intention for the day. The intention can be to observe, to learn, to listen, to lead, or simply to stay present. As you set this intention for the day, let your body respond to it. Notice if there are any changes in your breath, in your heartbeat, in your posture, and simply stay with it. Take a pause and just stay. Now, take 3 deep breaths. Inhale and exhale. Inhale and exhale. And one more time, inhale and slowly exhale. Begin to notice the sounds in your environment. What can you hear around you? Can you hear my voice? Can you hear the sound of the fan or the AC? just bring your attention slowly back to the sounds around you. Notice what the temperature of the room feels like. Is it cold? Is it hot? Or is it just about right? Notice how you're sitting and very gently shift your posture just a little bit. Just a little bit. And you can gently rub your palms together. Slowly in your own time, put them on your eyes and open your eyes when you're ready. Welcome.
Thank you, Akanksha ma'am. We are delighted to begin this day by extending a warm welcome on behalf of our school. To begin with, we would like to invite our Vice Principal, Mrs. Sameer Arora, to come to the stage and deliver his welcome address. Sameer sir, if you could please join me on the stage.
I'm that student who's entered examination hall and didn't sleep whole night and so underprepared. Thank you, Monica ma'am, for the opportunity to be here. On behalf of our chairman, Mr. Shikhar Malhotra, our CEO, Colonel Gopal, CEO, Bisarthi Davo, and everybody else in the senior leadership team, I invite you all to Shiv Nadar School. And, it's interesting to see that how many of you have taken out time on a Tuesday morning to come to the Physics Conclave. This talks about your enthusiasm about unraveling the mysteries of the universe and particle physics. But I thought before we embark on this journey of self-discovery and discovery, it is important to take a moment of reflection and think that how profoundly and deeply there is an interconnectedness at the heart of science, history, art, economics, or academia. And as the world becomes more complex, this interdisciplinarity becomes more profound. And we know today, if you look around, the knowledge does not exist in silos. We also see that we look at the world as beautifully interwoven tapestry, of which each discipline is a unique thread, which is coming together to form this beautiful, human existence. And coming to that point, it's important that as you participate in this conclave, do not just seek answers in science, seek answers of every discipline through science and with science and through the lens of different disciplines. And that is what is important. You also need to embrace the power of interdisciplinarity. When we were growing up, we had science, commerce, and humanities, and within science is non-medical and bio, and still continues to be in a lot of fields. But we also know that today, even ITs have started courses in interdisciplinarity, or what we call as liberal arts learning. And that's the way the future is going to be. Also embrace the richness of all this interconnectedness that comes together between seemingly unrelated concepts. Otherwise, you won't see what is between science and history. And here we have science historian talking about that, Dr. Janvi Falke. Give her a round of applause, And I think Dr. Archana will also be joining us shortly. The number of people at CERN who work are not necessarily all scientists. They're coming from diverse field. And that is the beauty of research and interconnectedness. So the whole request to all of you is that embrace the richness that comes from connecting the dots between seemingly unrelated concepts, for it is at the intersection of that knowledge that true insights are born. So take this day to collaborate, communicate, foster deeper relationships with different disciplines. And with that, I just would like to, highlight one key feature of this conference, that it's all led by women today. So I think a round of applause for all women. Shashi Banerjee, who's the Director of Education, who started the conversation. Vinita Sharath, who's a dear colleague and a friend, and I generally tell, don't quote me anywhere, she can beat science out of any humanities person. Ms. Monica Sagar, a Director Principal, who's an economist and is a excellent teacher for economics, but she's always advocating for science. And a lot of my colleagues here. So here's to women power, to wonderful women who worked in the fields of science and history, Dr. Falke and Dr. Archana. Round of applause for women in STEAM. Just a bit about Dr. Archana. I have known her for almost 12 years. I first met her, she came across a very passionate and a strong woman who's advocating science. She does advocate for science, but she wonderfully talks about interdisciplinarity and the role of all disciplines in the field of science. She's also been bestowed wonderful awards by the Government of India. We will talk about that in a short video we made on her life. And here, Dr. Janvi Falke, whose work I've been following for 4 years. She's science historian, founding director of Science Gallery Bangalore, which is a part of the prestigious 7 Science Gallery network around the world. So let's take our time to have conversations, to meet each other, and sort of form deeper bond for future collaboration. This conclave doesn't end here, it begins here. Thank you, children, and thank you, everyone. Welcome once again.
Thank you, Samir sir. That was truly inspiring. We would now like to take this opportunity to welcome our very own passionate physics enthusiast and central program lead for STEAM and science, Ms. Vinita Sharath. We invite Ms. Sharath to the stage to share a few words of welcome.
Dear August gathering, our own Anju ma'am from Faridabad campus and Monica ma'am, Samir, and all my dear friends from different schools, students, teachers, and Shiv Nadar school students. You know, there are 2 things which I would like to highlight on. The speakers of the day, about the speakers of the day, Dr. Janvi Falke and Dr. Archana Sharma. These 2 are leading ladies in the field of STEM, or you can say STEAM. I would not like to speak more about them because I know people know about them. They are very passionate science and STEM people. They will come on stage and then you will realize what change they have made in your life in just one day. And I'm serious about it. Okay? I'm really serious because, you know, I remember my day when I was sitting in audience 12 years back at Miranda College, and Dr. Archana Sharma was connecting virtually from CERN. And it was a day when she said, any questions? And there were almost 1,000 professors, teachers, and there was one school which was, at that time I was in different school, was my school and myself. And I asked that you say that, you know, students are not taking pure science and we have less scientists. What people sitting at CERN, Bhava, and other scientific organizations are doing about this? Can we come to CERN? Her answer was, it's for higher education children. I said, so when children are at 9th grade and 10th, if they come and they interact, they see what actually you guys are doing, obviously they will be pursuing career in pure science. And that was a day with this single question, I got connected with Dr. Archana Sharma. And that was a time when Mr. Samir, who was then having a partner, you know, running a company at, he came to me and he wanted me to go to NASA. I said, no, I would like to go to CERN. He said, no, we only provide NASA. I said, no, I would like to go to CERN. That time Big Bang Theory had come and I was after him. So he changed the whole program. And I believe this was the first time when Samir or any Indian school went to CERN for a workshop. So I just want to focus on one thing. How did this miracle happen that my connections with, you know, with so many students and primarily with Dr. Archana Sharma, and I've been going CERN almost every year since last so many years, was just because I asked a question. So be very, you know, interactive when Janvi Falke take your session, Dr. Archana Sharma speak about it, because the more you get involved, right kind of question you may ask. Okay? This is very important to listen very carefully because you don't know what will change in your life. I see many students of mine sitting at Harvard, Stanford, doing particle physics and astrophysics because I was passionate. Because, you know, the school had given me freedom to go beyond boundaries. And that passion I can see in many students who have come today. So get involved in all the session. Whatever you are getting today, I'm sure you will not get easily. It is very easy to say we can see on YouTube. Yes, you can. But can you speak? Can you interact with the scientists? No, you can't. Okay? So be passionate, be very active, be a listener. Do not lose any chance if there is a relevant question. Raise your hands, we all are there, and ask. The second thing which is most important is just to reflect on the nature of knowledge and on how we know what we claim to know. Who can be better speaker than Dr. Janvi Falke, who has researched, who has married history with science? You think that E is equal to MC square was one person credit? No, it was not. You go deep in that book, you go read more and you will understand what was the history behind the making of E is equal to MC square. So this is my second point which I want to emphasize and reiterate so that it embeds in your mind, okay? Take it politely from my side, but firmly. Do not accept everything which is given in the textbook. Do not accept everything what your teacher says. It is very important to deep dive. Go research, ask in your mind, read books, find the making of E is equal to MC square. Just do not solve numerical on E is equal to MC square. These are my last words. Thank you very much. I hope I made a sense to my little young minds because I really mean I would like to see many of you taking pure science. And obviously now the subjects are not taught in silos and you will understand the importance of science and social science and history and how can you be better scientists if you know art. One last thing, if you see these banners, they are official banners of CERN. And every year whenever Dr. Archana comes, these banners come with her. These all are made at CERN by the artist. And I was amazed when I went there and I came to know that 90% staff of CERN are from non-science background. Can you imagine? So they want to, you know, make general people understand the Big Bang theory, the origin of universe by these paintings. Okay? So again, today is the Dem of STEM and we all are celebrating STEM with the two leading ladies. I do not want to waste time with my speech. Thank you very much. Over to you.
Thank you, Vinita ma'am. I'm sure your words have triggered the curiosity and enthusiasm of everyone in the audience. Before we proceed any further, we should gain some more insight into the world of particle physics and the significance it has in the modern era. I would like to invite Amol Grover from grade 10 to give a short talk on particle physics.
Hello, my name is Amog and I'll be giving a short brief on particle physics. Physics. It has been defined by many scientists over the years. Some say it is a science of matter, while others refer to it as a science of energy. But really, physics is the understanding of the universe. We live in a supermassive realm of space, time, and matter. The study of the basic building blocks that make up this beautiful realm we live in is known as particle physics. Particle physics studies the fundamental particles of matter and energy. These types of particles are on an incomprehensibly small scale. The field seeks to understand the fundamental forces and interactions that govern the behavior of these particles and the nature of their interactions. To study these tiny particles, scientists use massive devices like the Large Hadron Collider, LHC. The LHC, which spans under Switzerland and France, accelerates particles at nearly the speed of light and smashes them together to reveal their composition. Despite their invisibility, the study of these particles has led to remarkable real-world applications. Medical treatments like hadron therapy and electron radiotherapy are at the forefront of fighting cancer, and they have been developed thanks to these experiments. Additionally, particle physics technology has contributed to the creation of advanced 3D color X-ray scanners. These are just some of the new developments made in science and technology with the help of this field. Particle physics keeps revealing the mysteries of the cosmos, stretching the limits of human comprehension, and opening the door to groundbreaking discoveries and useful applications that advance humankind. As particle physicists continue their quest to unlock nature's mystery, they inspire progress and open new possibilities for the future. Thank you.
Thank you, Amog. Now, we are honored to have Dr. Janvi Falke, the founding director of Science Gallery Bangalore, to share her insights on the role of science in our everyday lives. Dr. Falke will explore how scientific discoveries, especially in the domain of particle physics, shape our world and enhance our understanding of the universe. Join us for an engaging session that bridges the gap between science and culture. I request Ms. Monica Sagar and Ms. Anju Wal to facilitate Dr. Janvi Falke and present her with a token of our appreciation.
Okay. Good morning. Uh, Thank you very much for inviting me to speak with all of you. This is a wonderful opportunity. Let me start by saying that it's been a long time since I was in school. It's been 35 years, to be precise. And I haven't been back in school since. I did have a teaching career, but I was teaching in a university, not in school. In fact, once I left school, I really did not want to go back to school at all. When I was a very young child, in fact, there's a story, it's a family legend. I mean, there's some kernel of truth to it, but it's not, because I have no memory. It's a story from when I was 3.5, when I actually ran away to school. I really wanted to be in school with kids who were growing up and wanted to study with them and, read and write. By the time I was 15, I was ready to go. So At this moment, I think what I want you all to realize is that there are many things about which you know far more than I do, because you're very close to what is considered fundamental in many disciplines, which adults forget as they start living lives, and their knowledge of the world around them, in fact, gets narrower and narrower and narrower. So when I was teaching at King's College in London, I used to often spend a lot of time in the British Library, and there they had a series of books which were called Things I Used to Know. And they were put together for adults to remind them of what they learnt in school. So they were literally like textbooks, but written in bite-sized ways such that adults would understand. So not in the complicated way in which you read it, but in sort of, much more easy sort of paragraphs, so that you just remind yourself, and then you hopefully go back to what you have forgotten. So I'd like you to know that this is probably the time you will know a reasonable amount of very many things, which will very soon begin to deepen, but also get narrow. And so this is a time to enjoy what you know, enjoy what you're learning, also pick from it what drives your passion, and then take it forward. Most of you in this room are also privileged that you go to good schools, you have good teachers, you have opportunities such as this one, but also many others, to be able to pursue your passions, but also identify your passions, right? So I know it sounds like a little bit of early morning gyan. I'll put that aside and I'll come to the real stuff now. Okay, so a little bit about this morning. What I'll do is I'll speak to you in these three sort of sections. I'll speak a little bit about my own journey to becoming a historian of science. From that, I'll move on to a little bit about why I felt that research needs to be in the public domain, and in what way. And then after that, we'll have a question-answer session. So and I'm going to try and keep it equal so that you get to ask me as many questions as you would like to ask. So here's the thing. As I was leaving school, the year that I left school, so I studied in Bombay. There were a series of lectures at the Tata Institute of Fundamental Research, where I learned about things that researchers were, delving into in depth, the kinds of things that you will hear from Dr. Sharma after myself. And I was really excited by the stuff I heard. In fact, I thought it might not be a bad idea to become a physicist. And then when it came to actually going and taking, deciding what I wanted to do, I remember the day my father handed over to me, and this will date me hugely in your eyes, a 500 rupee, he gave me 500 rupees, and he said, go get yourself admitted to whatever college you want to, in whatever discipline you want to. That money went very far when I was young. But also, in the state where I studied, Maharashtra, girls did not have to pay school fees or tuition fees until their first degree, which was actually quite a fabulous thing, and it allowed for many people, to get higher education. So anyway, at that point, with my 500 rupees, I went to Elphinstone College and got myself admitted into a humanities program with history, economics, and political science as my subjects. I have absolutely no idea why at that moment I had an amnesia and I did not decide to enroll myself for physics. With, of course, you should of course know that I did have the grades to get admitted to physics, but I didn't. And I spent the next 5 years getting my first degree, so +2 I did in college, not in school, unlike, I think it's in the north that the +2 is more in schools. As you go more south, the +2 begins to be in colleges. And then, so for 5, I got my first degree. In the final year, I did what again here you call an honors degree in civics and politics. I got a master's degree in civics and politics. at the University of London, and then I started working on a doctoral program, and I started working on my PhD. Because at that point, I was fairly certain that I wanted to die a professor. Like, I would consider my life unfulfilled if I did not become a professor before I died. You know, it's a little difficult to imagine a 20-something person, which of course is way ahead of you. For you guys, it's still 10 years ahead of you. To think of, you know, what one would want to spend one's life doing. And it was, I think, about a year into my PhD program that I realized I just wasn't happy. And I wanted to do something else altogether. And so I'm cutting a long story rather short. Of course, I'm sure you don't believe that because you're already bored. Because none of you are smiling. No, some of you are. Okay, good. So, so I decided that I was going to leave it all behind me and I was going to start my education all over again and re-educate myself. And among the programs that I applied to was a program in history of science in the United States, because that's possibly right now the only system that allows for you to transition from any discipline to any discipline, provided, of course, you're willing to put in the hours and move ahead. And so I found myself at the Georgia Institute of Technology in Atlanta in a program in history of science, taking undergraduate courses in physics, training myself in all sorts of things which I'd never learned before. And a few years later, I graduated with, well, what I should say is that in the first 6 months, I knew I had arrived home. I absolutely fell in love with what I was doing. There wasn't a moment that was boring, to the point where my cohort and I would be found so we were 6 of us in the PhD program. We would be found hanging out in my office, because I was the privileged one with an office because I was a teaching assistant. And we would just read and talk and watch things, and we would do that, and then 7 in the morning, suddenly it was like, oh shoot, 10 o'clock is class, we need to go shower and come back. And it went on like that for about 3 years, after which I picked up my research. Now here's a little bit about what history of science is, right? Again, so if you look at how I'm going to speak to you today morning, right, like history of science, so my approach to science, so to speak, right? So by now you've gathered that I come to science from the humanities. I shifted to science from the humanities. My perspective on science is also from the humanities. I do history of science, right? So that's one. And then I also the other thing I tried to do was to put research into the public domain, which meant that I actually made a film about a cyclotron, a baby cyclotron, which is sort of the how do you call it, among the very first ones that was built, of which CERN is now the sort of successor, right? So the principles on which CERN is based is that of a cyclical particle accelerator, and my first film is about a particle accelerator, which is the world's oldest functional accelerator and I'll come to that in a second. But so there are 3 things again. So I like to work in 3s. So history of science as approaching it through humanities, through filmmaking, and then through public engagement by the kind of work I do with Science Gallery Bangalore. So history of science as a discipline is not, unfortunately, offered in any university in India for a degree program. You have a few programs that offer a few courses here and there, but it's time, I think, that we developed a program of this kind. Let's see what happens in the next years. What is it that historians of science do? So the way we are trained in history of science is that the first sort of, perspective that one needs to have is to understand that modern science, or what we today call science, has a history of about 400 odd years. Right? So it's that short, right? That doesn't mean people did not have knowledge systems before that, systematic knowledge systems before that. There has been systematic knowledge production about the physical world around us, including the cosmos that Archana will speak about later. But what we today call science, is with its methods and with its place in the world, along with its cultural authority, right? Ask me a question about this later, and I'll tell you even more. What we understand today as science in terms of the most reliable, the most credible knowledge about this world is a new thing, right? And it is, the history of science largely looks at this period. Of course, there's a debate about what do you call knowledge, systematic knowledge produced before this time, and what is the status of that knowledge. So that's one sort of thing that history of science does, right? Like to create a sense of what it is to know, what it is to understand the physical world around us. So that's one. And then within that, as historians of science, we specialize in different kinds of things, right? Like, so for myself, for example, I became a historian of the long 20th century, which means late 19th to the early 21st century. That's called the long 20th century, looking at largely the physical sciences, because that's what excited me. And others do other things, historians of biology, historians of astronomy, historians of statistics, historians of a range of things, right? But you do need to specialize, just like people who do scientific research specialize, historians of science also specialize, right? Now, the thing I want you to note here, and maybe some of you already did, because I'm told that this new generation is much smarter than, you know, that my generation was at this age, is that that moment when I was 14 and 15, when I thought physics was exciting, came back into my life in a very, very different way, without in a sort of direct way, right? Like, I didn't have to become a physicist, but I found a door to reach back to that excitement at a later stage in my life, right? So this is sort of, you know, the larger picture, so to speak. I'm happy to speak more to this as you might have more specific questions about why history of science, what history of science. I'll come now to public engagement with science. Why does understanding science in the public domain matter? It matters for several reasons. The first of which is that today it's actually not possible even to do or to study or to pursue careers in disciplines that are not necessarily about science or technology. What do I mean by that? So, for example, if you wanted to study civics and politics like I did, when I was studying, you could understand electoral behavior in a very different way. You could, you know, it was all about ground practices, political party formation, how many seats in the parliament, how many constituencies, all of that, right? Today, you're not going to understand anything about electoral behavior or able to make any, how should we call it, robust claims about electoral behavior without understanding the presence of social media, agencies like Cambridge Analytica, and what they are doing in the domain of politics. Similarly, if you wanted to understand, so, you know, like every thinking young woman between the ages of 15 and 21, I was a radical feminist. You need to understand everything from your body to, you know, your need to understand, because you're growing and you have questions that most people around you are either not ready to answer or not willing to answer. And today, those questions are compounded with the kind of gene technologies, medical technologies, and other devices that are available to us. How do you take a call on, for example, all of you know about CRISPR-Cas technologies, right? These are no longer domains of research. These are domains of research that affect your day-to-day life and ask of you to make choices. Are you going to get going to get an intervention because you know you have a family history of X or Y? Are you going to get it tested at all? Is that going to become a condition for, you know, I mean, we are a country of largely arranged marriages. Is that going to become another thing that is required alongside some other documents, right? These are things, so science and technology is implicated today in day-to-day life in ways in which it was less so before, right? We carry our lives in our palms these days. We carry, we are able to access the world through our palms, in our palms today, which was not the case even when I was growing up. I first handled email when I was 23, right? I got my first email account at 23, yeah. Which means I had done the bulk of my growing up before the internet and all of these other sort of not just consequences, but products related to the internet came into my life, right? Whereas you guys are born into this world. As a result of which this is present, which means you do not, for example, just to give you a very quick example, when I needed information, or when my generation needed information, we went to the library. You just do it quickly in your palm. But it also means, when I went to the library, I knew someone had chosen those books, and those books were there for a reason, and those books had been vetted by somebody. What your generation, in a way, does not have necessarily at every time is that hand of guidance. Right? How do you discern a good source of information from a bad source of information? How do you discern malintent from good intent? How do you assess the quality of a piece of information or data that is thrown at you, be it scientific or otherwise? Because information today is in your life, right? In every which way. So this is what I mean by the ubiquity of research and research-led products, which includes technology, but not necessarily only technology. And therefore, the understanding of history of science, sociology of science, is in fact necessary irrespective of the profession you choose, because you're going to be making very critical decisions about your life. And that is where the desire to do public engagement for science was fueled for me. The opportunity came my way, and I'm very lucky to have it. And so I have put in the remaining good years of my life in setting up an institution. It'll drown me, eat me up, I think. So I'll say a little bit more about the gallery, after which please ask me as many questions as you want. Let me see if I'm able to work this. Usually I am. Okay. Yeah, there we go. What does this remind you of? I'm sure you recognize this very quickly. Come on, tell me, what is this? Yes? Huh? Say that again? It's okay. Can you say it a little loudly? It's a natural history museum. Yeah? It's a natural history museum. So, it's fine. Yeah. So basically, these were the first public spaces of knowledge in the world, right? It started out with a cabinet of curiosities which rich and aristocratic men would collect, and what did they collect? They collected curiosities from around the world, which meant, all of those things, taxidermy, botanical herbariums, etc., etc., etc. A collection of samples of interesting things from across the world in order to understand and classify, to create systematic knowledge about these things, right? So exploration, imperialism is deeply embedded in the collection and systematization of knowledge. These were the kinds of spaces in which this knowledge was created. Now, the interesting thing about early museums is that what is it? The object of scientific study, right? So what it is you're studying? A piece of rock, an animal, a botanical sample, what have you, right? Languages, sometimes even, the dead, the mummies from Egypt and the mummies from Peru, etc., right? So these things are all collected from across the world and studied in the self-same space. This is the space where the object of scientific inquiry, the scientists themselves, and the public occupy. So the public knows what the scientist is studying, they have an overview on what is being studied, and they understand that this is what science is about. So they have a relationship to knowledge making. They have a very direct relationship, in fact. So this is share, that we are understanding the world and let us share this with you, right? So this is the nature of early science, early public spaces for science. This has since, of course, gone lost. And, no, that is the wrong one. This is the correct one. This has since, gone lost. And why has it gone lost? Is because for various reasons, we don't collect samples anymore. Imperialism is not quite the order of the day in the same way. It is in another way. Happy to speak to it later. But also the object of scientific inquiry itself has changed. As, Archana will tell us very soon, it has become more and more and more abstracted. There were, of course, abstractions before too, but science itself has become more collaborative, less individualistic, extremely largely funded, and the public has been pushed out of spaces of knowledge making. So the public no longer has access to or an overview on what is being studied for good reasons, good meaning, good logistical reasons, right? So the public's now left out. Now, at the same time, there has been, you can see, especially in the last 50 to 60 years, there's also been a transition of the museum space then becoming a pedagogical space. Not a research space, a pedagogical space. What do I mean by pedagogical? So instead of showing you the objects of research, we got more and more science centers that started teaching you concepts in science. Go push a few buttons, understand about gravity, put your hand on a copper plate, understand about X, put a thing in, run this experiment and understand principles of Y. Do this and you'll understand, Newton. So they have become places of didactics. It's a place to go and understand science. The understanding, of course, is happening somewhere else. It's not happening in those same spaces. So museums transitioned more and more towards science centers, scientific research moved more and more into closed institutions in universities and elsewhere. So we go and we see this object now, but the people who are studying them are no longer in the same space. Now, of course, it is not true absolutely everywhere. There are still some, especially natural history museums where research is carried out, especially the very large ones like the Smithsonian, the Natural History Museum, in Berlin and in London, but they are far and few in between. Now, these spaces that had objects that were being studied in the past also had objects that might be today considered objects of the humanities, right? So they had mummies, for example, they had ritual objects. So if you go to a British museum today, or if you go to a comparable museum, you'll find that they also have objects that give you more information on the human civilization, right? And so you understand a lot of also what is being studied by the humanities. What does that tell us? It tells us that before, well, about 120, 130 years ago, there was natural philosophy and there was moral philosophy. They weren't the kind of separated out, siloed disciplines that we see today. We learn this from history of science. Physics emerges only in the late 19th century, so on and so forth, right? And so, what has happened in this process as the museum separates out from the research, disciplines get formed, humanities get written out of the larger sort of domain of science. Not all over and not across the globe. This is, again, we need to remember, a very Anglo-American phenomenon. So if you go to Germany or German-speaking countries or French-speaking countries, when they say Science or Wissenschaft, what they mean is the human, social, and natural sciences, right? That doesn't, of course, mean this hierarchy or of cultural cultural authority being largely, strongly in favor of the natural sciences and not in favor of other sciences. But this, the divide in a way is much stronger in the Anglo-American world. So these kinds of objects and the wonder that comes with them is written out of our understanding of what systematic knowledge production means. Okay. Is it me? Is it? Yeah. So, in India, this is a lovely old picture of the Indian Institute of Science in Bangalore, India's first major research institution. In India, as we all know, this divide is actually extremely strong. Your generation is still lucky, and as I understand from your teachers, that there is great effort to actually bridge this divide and to give students the choice that goes beyond what is normally offered in the Indian schooling system. That having said, once you leave the school, the system again puts you into silos, right? So between the ages of 15 and 17, all of you will have made choices, and then if you stay on in India, engineers will study with engineers, doctors will study with doctors, architects will study with architects, and humanities scholars will study with humanities scholars. As a result of which, and this I want you to remember very well, is that when you go away in your best years and spend those 4 to 5 years with people studying, often in a residential campus, you have no access to the minds of people who are thinking about other things. You might still change your profession after that. But if you're studying engineering, you never meet a historian with whom you eat food. You never date an artist. You never, fight with an accountant, and heaven forbid, fighting with a lawyer. But so you see what I mean? That you never meet people whose minds are being formed like your own mind, but who are not in the same professional training courses as you yourself are. As a result of which you really do not grow up, you as in us, do not grow up appreciating what it takes to become a historian, what it takes to become a physicist, what it takes. So likewise, right? So when we say people in the natural sciences in India seldom show respect for people who come from the humanities, the reverse is also true. While the cultural authority may stay, a historian has no appreciation for how an engineering person thinks. And not only that, you never get the chance to puncture these ideas, right? Like to fight with those ideas and say, you can't actually design an urban waterway system without understanding how urban people use water, for example. Right? You can't say that to an engineer because the engineer is not sitting next to you and eating food. And so you can't throw your apple at them, right? Or you can't throw whatever at them and say, you idiot. So this conversation is stunted. This conversation across disciplines simply does not happen, and this has consequences. This has consequences for decision making. This has consequences for the kinds of buildings our architects build. This has consequences for the kinds of histories our people write. We are all impoverished for it. We are all poorer for it. And this has to change, right? So, this is my second point of departure for how and why I think about public engagement with science the way I do. In the middle of a sea of lovely young women is a man, C.V. Raman. Let me see. There he is, where he is. You can see him, right? My pointer's not working. So I'm not able to work the pointer. Two different things. Now, C.V. Raman, some of you will know, and if you hear me speak, if you've heard me speak before, if you have the misfortune of hearing me speak again, you will hear me tell this story. Because it is very, very important to me for the kind of institution I want to set up. C.V. Raman, for the first 10 years of his professional life, was an accountant. He was working with the Indian Audits and Accounts Services, and in the evening, he would go to the laboratories of an institution called the Indian Association for Cultivation of Science in Calcutta, right? So here was someone who was an accountant but had the possibility of pursuing an idea passionately in a public lab in the evening. Today, this is impossible. Today, it's impossible to even think of having a public institution where you can actually pursue an idea simply because you're passionate about it, right? Of course, again, we are all aware that the nature of science has changed. the kinds of equipments that are required for science are changed. But that doesn't mean that people who are, say, accountants by day or engineers by day or, anything else by day still don't have the inkling of an idea that always bothered them. I mean, Raman's big idea was, the idea that bothered him and got him on this fabulous journey was, why is the sea blue? Now, such questions can arise in anybody's mind, right? And if they want to pursue it, where should they go? And that's the kind of institution I think we need. We might not be able to take that question to its fullest answer in the kind of labs we have can have in the public domain, because of course we can't replicate CERN now, for example, right? But we might be able to work with someone who has a passionate idea to reach a question, right? Like to what by now you might have understood as define a good problem or ask a good question, right? So we can work with them to be able to identify a good question which can be then taken to a university lab or an incubator or a wherever, right? Like where it belongs. But can we help ask good questions by talking to each other? And I think that's the kind of new institution we need today, a new kind of public space for science, which is a two-way bridge between the public and research, where research is engaging the public. It tells them, why, for example, everybody doesn't need to become a quantum physicist, right? But it is important that all of us understand how quantum physics, for example, affects our everyday life. Everyone doesn't need to become a biologist or a genetic engineer or, or do genetic biology or research, but we need to understand why CRISPR-Cas matters to our everyday lives, not only as human beings, but also what we consume and what it does in plant genetics, for example. So these are the kinds of things, right? Like that we need public spaces that allow for knowledge to thrive, to be shared, but also to be shaped. What is it that we want to know? Do we have any fora for us to be able to articulate that, right? And this is the kind of space that we need today. So Science Gallery Bangalore is one such design, one such institution. We need many such efforts. We are a part of an international network, as Samir already said at the start, of 7 galleries across the world, 4 in Europe, 1 in the United States, 1 in Mexico, 1 in Australia. In Bangalore, we work very closely with academic partners, which is the Indian Institute of Science, National Center for Biological Sciences, and the School of Design. These are the 3 operative words. So what is it that, when I say we should know and we should be able to engage with it, what I mean is that we make science cultural, because that's where it belongs. When we say science and a society, there's a problem there. Is science outside of society? Are scientists not social creatures and citizens? So it's the rendering of science as culture. It's sort of making people understand that science is also about culture, or that science is cultural. That's the kind of work we need to do. And this institution is an experiment because it's a new kind of institution. But also, experiment gets a new flavor in our work, because we have something called a public lab complex for the kind of work that I just spoke about, for someone who's passionate about an idea and wants to develop it into a proper research project, a proper research proposal which can be taken elsewhere. We work, of course, with young adults, target age group 15 to 30, 15 to 28. These are the 3 things we do: public engagement, which is largely research festivals, public lab complex that I just spoke about, and mentorship initiatives where we have apprentices, mediators, and a range of young adults who work with us in order to sort of break the silos. So what we do, for example, in research festivals is we take one object remember I spoke about creating a relationship between public and the object of scientific inquiry. We pick our topics as sort of, ideas that might be explored by different disciplines, and then we bring a set of disciplines to speak to it. So for example, when we did a research festival on contagion, we had epidemiologists, vaccine makers, vaccine activists, historians of medicine, filmmakers, people who spoke about computer viruses, people who spoke about the contagious nature of laughter, the contagious nature of energy on a dance floor. So how do different disciplines think about transmission and contagion, right? That's the idea behind it. How do you bring different disciplines to speak through robust research and robust knowledge to the self-same idea? That's what we do in our research festivals. These are our this is our way of doing it, or one way of doing it. Okay. Okay. Clearly inept. And while this moves and or doesn't, let me. Yeah. Okay, I spoke about this, happy to take this up further when we move. The lab complex, these are the labs we have, 7 experimental spaces. These are the research festivals we've held so far. Their archives are on our website, but feel free to ask me questions about it as well. The last 3 were done online because pandemic. We work with cultural and research institutions, museum-like institutions and research institutions across the world. So these are some of our international partners, and when this moves again, you'll see some of our Indian partners. Okay, it's not wanting to move. Really doesn't like my fingerprint. You moved? Thank you. These are some of our Indian partners. We've worked with both the academies. You can move to the next one as well. And this is the building. It actually does look somewhat like this. It has been, this building carries, as I like to say, my blood, sweat and tears from the last 5 years. We open our doors this year. So of course, if you're in Bangalore, feel free to, visit, let me know. And now, shoot away. Ask me questions. Let me start by asking you a question. How many of you knew of the discipline of history of science? 1. Why do you know about it? Because you're a geek? Okay. Questions? Or did you come here wanting to only hear about particles? I know Archana will satisfy that desire for you. Yes, there's a young lady here who would like to ask a question.
Hi, thank you for allowing me to ask a question. I just wanted to ask, there is a lot of controversy. Like there's a quote that says that just because scientists can doesn't mean that the scientists should. And about the misuse of power that science gives us. So I just wanted to ask, do you think there's anything like too much science?
No, I don't think there is any such thing as too much science. And we say use and misuse, right? Like, so these are very, these aren't categorical sort of things, right? So let's use the example, I'm sure most of you have or are going to see Oppenheimer already. Yeah. I strongly suggest you also temper it with, as I said, watching the Barbie film as well. Because, we all need to be culture, remember that. No, so if you see, the discovery of fission was in 1939, right? Lisa Meitner and Otto Hahn, which is the year that the Second World War broke out. Now, if this discovery was made during peacetime, we would have seen that over the next, any discovery to its potential presence in the world through technology, first of all, is not a linear path, right? And when it happens, it takes years because of the kind of investments that are required to make these things work. What happened instead, because it was wartime, is that massive amounts of money and political will was put behind the making of the atomic bomb. It took, it took hundreds of thousands of human beings, researchers, resources, materials to make the bomb. one cannot imagine that during peacetime such an enterprise would have even been taken up. We would have probably had the development of nuclear energy over a few decades before any such thing. We would always know the potential of it, because with fission we knew a bomb could be made, right? But that, whether it would have been made is a very different question. And so what happens is that there are moments in time when crises, so if, I mean another moment in time when a crisis triggered the presence of a research-based technology in the public domain is during the pandemic, with the mRNA vaccines, for example, right? Like the kind of pressure that was put on putting things out, of course, which there were several decades, if not at least two, of research behind it. Similarly for nuclear fission, I mean, nuclear physics as a discipline in a way took off in the early 1930s, right? So there is work behind it, but crisis propels things forward, and the use is propelled by that crisis, right? So in itself, so there's a lovely, Melvin Kranzberg, who's a historian of technology, said something quite interesting. He said, he speaks of technology, but I think we can also speak similarly about scientific research, is that technology is neither good, nor bad, nor neutral, right? So it's not good, it's not bad, but it's also not neutral. It is always dependent on the context in which it is produced, right? And what converges, right? Like who wants it to be used, who is promoting it, who is putting money into it, all determines how things are put out in the public domain, right? And so that doesn't in any way, so there's nothing preemptive about it, right? So it's a complex question, but there is no such thing as too much science, I think, because, you know, otherwise, if Newton wasn't working hard during the plague, when the plague was raging, for example, we wouldn't have some of the interesting observations he made, and, you know, we wouldn't have made that progress. So I think when you have a good question, you should run after it, you should try and understand it, but also be aware of the context, and that's why understanding, so, you know, society, history, politics is very important for someone who is a practitioner of science and engineering. So you should know what you're doing and why you're doing it.
Okay, thank you.
Thanks. Yes.
Thank you very much, audience. We are running short of time. The virtual visit of CERN is due at 11:25, but we can take one last question. Okay, just coming.
Yeah. Yes.
Hi, so I wanted to ask why history of science and how you got the opportunity to go into that field, because it's not something that you see advertised a lot.
Yeah, it's not advertised, it was random and it was by chance that I came across this program, and then I applied for it, and then I actually got the funding, and I have no idea why they thought I was worth funding, and, you know. So there's a lot of place for chance in everything you do in life. I did have a few other options, but this was the strangest of them all, and I took it up. Yeah? Should we take one more question from the young man at the back?
Ma'am.
Yeah.
One last question. Okay.
Yeah, you shared how you studied in detail, like the history of science of the 20th century. Can you please mention something about like some other timeline?
What would you like me to mention?
For example, like the 19th century, the 18th century, something about that, of like the history of science.
Oh, but I see what you mean.
Very good
would be
question.
very hard. I mean, I can take the escape route and save time for all of us and say that's not what I do, and so I don't know anything about it. But you know, so if you look at the 17th century to the 19th century, largely it is a history of imperialism, exploration, and how scientific research, in a sense, was conducted by empires for purposes that related to both commerce and knowledge making, right? Like, so those things are intertwined. Why do you study? So if you look at, for example, the volumes called Wealth of India, Moral and Material Wealth of India, which were produced by the British Indian government, you know, through, most certainly after 1857 and a little sort of more dispersed before that. Why do you want to understand the zoology, the botany, the archaeology, the geology of these continents? Is because you want to know what kind of minerals are present here, what kind of natural resources are available here, what are the fauna available here, right? And why do you want to understand astronomy from different locations? Because you want to be able to navigate globally, right? So the history of the development of modern science and modern technology is deeply implicated. They are not separate at all. People who are officers of the East India Company, the Dutch East India Company, and so on and so forth, are the people who are studying the skies and the waters and the animals and the plants and the minerals in order to use these lands as commercial materials, right? There are very interesting histories written about this time called Commodities of Empire. Cultural histories of this time, like if you look at Amitav Ghosh's The Nutmeg's Curse, for example, right? So you can understand why things were being studied in depth. And that's not to reduce it to say it's that they were studying it because they wanted to commercially exploit. No, those two. The thing is, you wouldn't be able to commercially exploit it if you didn't know it well. But at the same time, you wouldn't be able to study it well if there wasn't the motivation to actually use something. So as a result of which a lot got studied. Why map? Why did George Everest map India trigonometrically, right? It's in order to understand what the magnitude and measure of this subcontinent was, because political control was important. Knowing so knowledge is power, right? As good old Francis Bacon said. And so when you know something, you in a way have power over it. It's like also with people. If you know your friend very well, you know how to push her buttons, right? You know how to get under her skin, you know how to, etc. So knowledge is power in different ways. It's both political and commercial power, which is true also today. So if you understand 5G very well, you know how to surveil very well, right? If you know social media very well, you know how to manipulate electoral politics very well. That doesn't mean a lot of good. What do I mean by good? That doesn't mean a lot, that not, sorry, it doesn't mean that before this, there were people who spent hours and extremely interesting hours trying to understand a sweet problem in computing, in coding, right? So these things are always implicated. It's the implications that you need to understand. Where does knowledge converge with power? And how it manifests. In different times, in different contexts, it will manifest itself in different ways. Thank you. Thanks for your attention.
Thank you, Dr. Falke, for that engaging session. Now it's time for the Rindar STEAM competition. I request the participants who are taking part in it to head to the gate of the WCH. All participants.
Only the students participating in the Rangda STEAM competition should head to the main gate of the WCH.
Students who are participating in Rangda competition, start walking backwards. The teams will take you there. Teachers, I know the students did not get an opportunity to ask questions from Dr. Falke. If you email these questions to us, we'll make sure we make a personal connection and your questions get answered.
Students, you are going to have now a panel discussion where you will have on stage.
I'm sure Dr. Falke's session has set our grey cells on fire. To keep this fire burning, we now have a dynamic panel discussion to explore the complex interplay of science, economy, academia, history, and their connection to particle physics. Our respective panel of experts will shed light on how scientific advancements in particle physics have not only transformed our understanding of the universe, but also influenced economies, academic pursuits, and our shared historical narrative. We would like to welcome our panelists, Dr. Archana Sharma, Dr. Janvi Falke, Ms. Neha Bhatnagar, Ms. Sharmistha Mukherjee, Mr. Rahul Agarwal, and Mr. Uday Singh. Join us for an engaging conversation that unravels the intricate relationships between these domains, fostering innovation, progress, and a broader perspective on the wonders of particle physics.
A very good morning to one and all. Here we're going to discuss the interplay of science, economy, academia, and history. Four subjects that seem so far away from each other. But what do you know? Are they closer than you think they are? That's what we're here to find out. So, good morning to all the panelists. I'm Abhimanyu. I'm going to be your moderator for today. And I'm going to start with one question that I would like all of you to give your thoughts on, which is, in the ever-evolving landscape of human progress, the interplay of science, economy, academia, and history shapes the trajectory of our societies. Each domain influences and responds to others, contributing to our collective growth and challenges. As experts in your respective fields, how do you think these four pillars interact with each other, and how can we leverage this knowledge to create a more sustainable and prosperous future for all of humanity?
All right, am I audible? Okay, sounds like it. All right, so hi, my name is Uday, and I was a student in Shiv Nadar School, Noida, and it's a pleasure to be back here to answer your question without wasting time. I think I would like to talk about the intersection of science and history the most, because I feel like that is a multidisciplinary interaction that people take for granted and not really acknowledge a lot in their lives. But as Dr. Falke mentioned in her talk earlier, the intersection of how information is passed on and how it's deeply embedded in the history and culture that it comes from, especially in the field of science, is extremely important. And I can speak from experience because I work at the Georgia Tech Library. So Georgia Tech is the school that I go to, and I've been working as an assistant at the library for over a year now. And one of the things we worked on last year was studying how the library's informational resources have a relationship with the history of the institution. So Georgia Tech is one of the biggest science or STEM institutions in the American South, and as is the case with a lot of institutions in the American South, it was built by white people on the backs of a lot of minorities. And in more ways than you would expect, these ugly parts of history intersect with the type of information that gets passed on. And even if the information we're talking about is science and completely unrelated from humanities or cultural subjects, it plays a great role in biases that get transmitted from a generation to the next, or who gets credit for certain inventions or certain discoveries. Maybe back 100 years, a person from an African American descent would not be given credit for a discovery that they worked on, while a white person would get credit for it very quickly. And while that may not be the case, although that's also debatable now, the type of information that institutions like college libraries transmit are deeply embedded in the history of the institution. So I think that's something we must be very mindful about, that our history is extremely contextual to the science we produce, and the science we produce and transmit is not independent from what the past we come from. So yeah, I think that's my little bit of insight on that question. Yeah.
Thank you so much. I think I completely agree. There is so much interplay because everything we do in science and everything we do in economics comes from something that happened in our history.
Okay. Hello, I'm Archana Sharma, and it's great to be back here. Wonderful panelists and good questions. Of course, resources is something key to being able to do research and being able to do science. Clearly, in our country, we have a long history of philosophy, logic, mathematics, and science. Now, the way things are working, like Dr. Falke explained, that large collaborative mega science is the way science is proceeding. Now, how many of those mega science projects are we leading? Or how many of those projects are Indians leading in the world is the question. And then again, the reporting of that, the publications, the promptness with which publications that come out from a particular country will obviously be documented in the way the economy of the country works. So definitely we have a gap to fulfill there. And like you just said, that there are, I can give you an example of Dr. Biba Chaudhary, you might know, who did amazing work. I mean, I am literally disappointed, or rather, I should say my incompetence, that when I was doing my PhD, her work 40 years ago was beyond what I did in the 80s and the 90s. And she was not recognized. She was not even given a proper job in our country. She went to Manchester and she did some work over there on gaseous detectors, which is my field. She worked in Michigan. And Powell and somebody else, I don't remember the name now, got the Nobel Prize for the work that she did on discovering cosmic rays on her, the multi-wire chambers that she built. The meson, exactly. Now, that's extremely important to know, that how the reporting is done and what goes down in the history, how Nobel Prizes are given. So this is a narrative. If we collectively as Indians would like to take this forward, we have to come out in the open. We have to come to the front edge of this reporting, and people like Dr. Falke are extremely important in this, who are leading the crusade on the reporting for purposes of pedagogy and for purposes of historical documentation. So I think economy, history, and the cutting edge science, the mega science culture, all has to be well inserted in the minds of children like you all, so that you can take the crusade further. You know, we have just been thrown in the ocean of mega science projects. So we have learnt, like you just said, sorry to refer to you again and again, we just heard you. So we have been thrown in the ocean and we have learned to swim. But you are learning to swim in the swimming pool with teachers and instructors with the right rules and the right fair game procedures. So we will not be able to do, but we might be able to steer you in the direction which you are going to take the baton and run very fast.
Thank you so much, ma'am. I completely agree, and I am personally horrified at the fact that a true scientist who did so much work couldn't get the credit for it. But I think it's also a testament to how far our world has come now, that these things are changing and that this is no longer information that's covered up. So what about someone from this side of the panel? Would you have any inputs on how your specific fields interact with these 4 areas?
Okay, firstly, I would like to thank the Shiv Nadar School for bringing all of this together, and Bhimanyu, you're doing a fantastic job. I must commend that intersection of discipline is happening very early on in Shiv Nadar School already, because one of your students, my son, wants to become an astrodoc, an astronaut who's a doctor. Because his question was, Mama, who will treat the astronauts when they are flying up there? So thank you for bringing this idea of intersection. And Dr. Janvi, it was fantastic to hear you talk about, you know, when we were earlier on catching up, music and math. How do you connect music and math? Now I've been teaching my son ascending, descending numbers. How do you do that? Aro, avro, sare, gama, pada, nisa, sa, ni, dha, pa, ma, ga, re. So, you know, this is how you bring it all together. Now, why I'm giving a little pre-introduction is because I'm just probably raising the hand that I'm not a physicist or a scientist. I work for the Sustainable Development Goals of the United Nations. And we are basically trying to get international funds to invest in India and help the social causes in the process. And which is why I'm here to sort of give you an intersection in between all the 4 disciplines that we've been talking about: science, history, academia, and economy. Now, maybe you can imagine yourself sitting in your hall in your drawing room with your grandparents, your mom, your dad, and yourself. Your grandparents bring in the history, your mom brings in the science, your dad probably economy, and you bring in academia. This is something that you do every day in your rooms, your halls. Now let me go back to what I do. The biggest threat right now from where I come, Sustainable Development Goals, is climate. Climate threat is facing us. We know the history. There is enough history, enough proof to show that our lungs are not well, our animals are not well, our trees are not doing well. There is enough history to prove that. Now, we need science, we need solutions. Now, there is an example called Zero Cow Factory. It's a startup. So what my company does is we enable funds into startups to make a better India. So science is obviously a very important part of it. Artificial intelligence, robotics, it all plays a very important role. Now what they do is, Zero Cow Factory, they produce milk through biotechnology. The startup replicates cow's milk texture, nutrient profile, taste, and appearance by using an in-house developed technology. So this is just a small example of to show you that how science is meddling into helping climate or animals in some fashion. And of course, we need funding for the spectacular enterprises. And my co-panelist, Rahul, will be able to probably tap into that as well, because we both work in the same industry wherein we bring in a lot of money for the startup that are trying to make a difference in the country through science and machine learning and AI solutions. So, and at the end of it, academia, as I completely agree with Dr. Janvi, we need a lot of research, we need data analysis, we need deal flows, we need to understand how, if there is an impact being made on the floor, on the street, on the feet, the feet on the street, sorry, are making an impact. How are they doing it? Are we measuring the impact? How are we doing that? So let me stop here. I have thousands of examples I can go on, but over to you, Abhimanyu.
Thank you so much, ma'am. And I think you've led me directly into my next question, which is for Mr. Agarwal. So, sir, you have 22 years of experience in strategy development and investment planning, and also a deep understanding of the connection between economics and the impact of science on economic growth. So could you share your perspective on the role of science on economic growth of the world and also on the eradication of poverty?
Firstly, we need to understand what is this intersection of science, economics, poverty is all about. I'll just go through a few examples. If you look at what is poverty, and the definition that, while there are various definitions, one definition that resonates more with me is the deprivation of well-being. And when we are talking of well-being, we are looking at accessibility, availability, and affordability of basic services, be it health, be it nutrition, be it water and sanitation, be it housing. Now, if that has to be the starting point, you look at what has science contributed towards this juncture. But before looking at how the contribution of science, let's also look at the economic impact of not being so well-being. One study suggests that the economic burden of cancer is close to, and this is only in India, is close to $11 billion as of now. This includes the distress spending, which is actually going into the treatment of cancer, diagnosis of cancer. The second component is productivity loss, which is because you are not well, you are not able to contribute to any of the as a productive workforce. That itself is $6.7 billion. By 2030, this is going to be $30 billion. And if I quote a global economic burden, it is going to, by 2050, it is going to be $25 trillion. Now that's only cancer. Now how has science contributed to it? Particle physics, you look at from a diagnosis perspective, you have, and I'm sure my co-panelists know more than I do, but in terms of diagnosis, whether it is magnetic resonance imaging or you have positron emission therapy, all those aspects that have contributed to early diagnosis and to an extent wherein you are looking at a targeted treatment, they have looked at the treatment as well. Another example. And that's where I would like to now touch upon the history aspect. We all know there has been a war, Ukraine-Russia war. Now that is an event, it's a history. What has occurred as a result of that event? Today, 205 million people across countries are acutely food insecure. This is as of now. How has science contributed to it? While yes, there are various innovations that have been tested in the lab, but yes, there are various innovations that have been developed locally. We call them frugal innovations, we call them locally developed technologies. Now again, science has contributed to that extent. Whether it is in terms of housing, affordable housing, you have material innovations. So if you are looking at all these aspects, science has contributed tremendously. And one last point, and which also looks at the history, and I would like to expand the ambit to social sciences. While yes, there are technologies that are being developed, the adoption of technologies and what Dr. Falke, you pointed out, the use of that technology is also driven by the history. And if you look at the evolution of humans, how do an individual interact with the family? How do an individual interact with the community? How do an individual interact with the nation at large? What is shaping its behavior? Why is he or she behaving the way they are behaving today? It is important to understand that aspect as well. Unless we do understand the human psychology and the human behavior, and also that's where we have the socio-ecological model, unless we do that, we will not be able to enhance the adoption of technology. And that is where I do see a lot of career potential for these youngsters, because there's actually need for people who develop technology, people who take technology to scale, people who help adopt technology. So that's the intersection, and that's a huge career opportunity for everyone. Thank you.
Thank you so much, sir. And I think you've raised some really valid points, and you've really managed to spell out exactly how this intersection works. And I think that's something for all the students in the audience. I know not all of you may be fully, say, particle physics students. So you might be wondering, why am I at such a conclave? Why do I need this? And I think Rahul sir has been able to explain exactly how in your own fields of choice you will still be connected to science, and all of these subjects will be connected to each other. And that leads me to my next question for Sharmishtha ma'am. Ma'am, so as a journalist you have a unique vantage point at the intersection of journalism, economics and academia. So from that perspective, how do you see the symbiotic relationship between these four domains that we're discussing today? And how do you think they influence our current understanding of global challenges?
So as I see it, the interplay between science, economy, academia, history has always been at play, starting from the invention of the printing press. The invention of the printing press gave momentum to the Renaissance movement in Europe. It speeded up scientific discoveries. It is the first time after the invention of the printing press that knowledge could be reproduced and disseminated so quickly. Copernicus came up with the theory that the earth revolves around the sun after getting access to numerical data of other scientists. It led to the Reformation in the Catholic Church and eventually to the French Revolution. Now, standing today, this role of and this interplay between the various disciplines has become even more important given the existential question before us of sustainability
and climate change. So while science and technological innovations have always been the starting point of humanity and societal progress, what we should do now is, exercise the privilege we have of looking at history, putting all developments in context and moving forward in a way which will be balanced to create a sustainable future for us all. And also, given that climate change is having such drastic effects on all aspects of our lives, be it industry, be it government, be it academia, you and me, we are all thinking about it today. And this provides us with an opportunity to ensure economic growth in a manner that we use our resources more reasonably and responsibly while planning for our future.
Thank you so much, ma'am. And I completely agree, ma'am. The way information is circulated really helps science develop. And that brings me to my next question for Dr. Janvi. Janvi, ma'am, you talked so much about such varied aspects of where physics can come in our daily lives. But I want to ask you about your journey, because I understand you studied civics and politics at the University of Bombay and then at SOAS in London. So from there, now you've first of all got a vantage point into these subjects and their interplay with physics, right? But also now you run the science gallery. So where in your academic journey did you move from civics and politics to science? And I'm sure a lot of students here who aren't exactly sure what they want to do with their lives would also be really interested to hear this journey of yours.
Thank you. So I sort of mentioned it, in passing when I spoke earlier. It was a moment of dissatisfaction, right, with what I was doing. And I think, so it is an important point to be mentioned, not because I moved to science, but because I moved from somewhere where I was not happy professionally and personally to a place that eventually did make me extremely happy professionally and personally, right? It gave me a deeper satisfaction to be. Within 6 months, as I say, within 6 months of joining the History of Science program, I knew I had come home, right? And it sounds very melodramatic, but it's actually not. I felt it very deeply, right? I just knew this was just way too fascinating, right, for me. I mean, and to speak back, why does it make me happy? Because what were the kinds of connections I was able to make? So when we started our coursework in History of Science, suddenly Thomas Hobbes showed up. Now Thomas Hobbes is known to say sort of senior people who do political science or social science as the guy who called us our lives nasty, brutish and short. Now what we don't learn when we learn him in political philosophy is that he was a mathematician and a geometrician, actually not a mathematician but a geometrician. And he was deeply, deeply resentful of Robert Hooke, who spoke about the experimental method of verification of science, right? So here were human beings not very long ago who were perfectly fine. I mean, Da Vinci is of course cited always as sort of the great example, but there were others too who were who thought it was perfectly all right to do geometry and political philosophy and something else and draw and Newton worked at the mint, right? Einstein worked in the patent office. Raman, as I mentioned, was an accountant. So at what point, so if Raman was barely, was barely a century ago, right? Like, I mean, he was fairly alive, very close to before I was born. So if it was possible, then why have we kind of, made, and it was that moment of understanding. The other moment for me was that of that when we studied the history of statistics, 20th century statistics. And one of the strongest arguments that consolidated the establishment of the Indian National Congress in the late 19th century and then propelled the movement for independence and freedom of the Indian subcontinent was an argument made by Dadabhai Nauroji, who was incidentally also the first Indian to be elected to the British Parliament from Finsbury, which is where I lived, so I'm actually quite happy. I saw the blue plaque and everything. But he wrote this book called the Poverty and Un-British Rule of India. Now, what he's calling for is a moral argument. He's backing it up with numbers by saying these are the numbers of the British trade. This is the wealth that's flowing out of India, and this is what is being generated and given back to India. This is net loss. So how can this be a good thing? Right? This is a statistical argument in the context at a time when the idea of an economy is getting born. So political economy and a national economy is being born. National income accounting is being born. National income accounting, in fact, it doesn't happen properly until the beginnings of the 20th century, right? So you see how history, science, politics, resistance, anti-colonial movement, however we might want to describe, is actually just one and the same thing, right? You can say, I will speak to economic aspects of, well, you can, except you're leaving out a lot, right? So, but of course you need to disentangle in order to understand better, but it's always entangled. And I think it's that discovery of Hobbes being a geometrician and Dadabhai Naoroji being, working very closely with statisticians to make an argument for Indian independence, that convinced me that, this is probably a very, very interesting way to approach history writing. So that's been sort of, in short, my journey to doing this.
Thank you so much, ma'am. And I completely understand what you're saying. I myself am a student of both physics, chemistry and history, all three subjects that I really hold close to my heart. So I completely understand what you're saying. Also, fun fact for the audience, Thomas Hobbes that ma'am mentioned is also the one man who inspired the character of Hobbes from Calvin and Hobbes. So take that as you will. One final question for Dr. Archana. So Dr. Archana, you work at CERN, a place where most physics aspirants can only dream of working. And above that, you've been awarded by the President for your outstanding contributions to science as well. But despite that, you also engage with so many other fields in your work at CERN. And could you tell us a little more about how your work will impact these fields apart from physics?
Thank you for the question, and I will speak about it in my talk. So I'll be very brief right now. All of you have touched upon very important points, like the statistics for cancer, the cancer burden on our country. If you look at the numbers, it's like a country within a country of only cancer patients. That is dying day by day, and that is adding new countrymen who are cancer patients. So science has to come to the rescue, and in a very big way. We have to change the paradigm on how we do things. So perhaps it's the topic of another panel discussion or a longer talk where we want to address how this change can happen. Because technologies are running very fast. Dr. Falke showed one map of the science academies of the world. We can look at the cancer facilities in the world, and you draw a line from the north of India, which means way above Kashmir, you draw a straight line and all the facilities are in the north. What's happening in the south? There comes history, there comes poverty, there comes development and science and technology. So we need another discussion, and it's extremely important, and I want to know the source from where you quoted the numbers of the economic burden. You spoke about sustained development, climate change, and all those problems will be solved by those students sitting on the benches in front. In our lifetime, we have understood the problems to a point where we could perhaps articulate how the solutions could come. But even that is not clear in our minds. So the high school student today is going to be the scientist of tomorrow, and who will be facing these challenges and finding the solution with the help of science and technology. So I'll stop here because I'll speak more about this in my talk. Thank you.
Thank you so much, ma'am, and thank you to all of our panelists. I know all of us really want to hear a lot more from these panelists, and there's so much more to discuss, but unfortunately that's all for today. Thank you all the panelists for your thoughts and for guiding us through what are such complicated fields, and you've made them so easy for all of us to understand. Fields that may be foreign to some students as well have become so easy, all thanks to you. So a big thank you. Can we have another round of applause for all of the panelists, please?
As we conclude this thought-provoking panel discussion, we extend our sincere gratitude to our esteemed panelists for their exceptional insights. Now, I would like to introduce a very special guest, without whom this event would not have been possible. Yes, it is Dr. Archana Sharma. We would like to show you all a short video about her life. I request Ms. Monica Sagar, Ms. Vinita Sharath, and Dr. Falke to facilitate Dr. Archana Sharma. We request all the panelists to please remain on stage. Thank you.
With your permission, comparers, may I request my student Uday to felicitate Dr. Archana Sharma. He is student of Shiv Nadar School and presently pursuing career in physics at Georgia Tech. Thank you.
I would like to thank all the panelists. Their contributions have enriched our understanding of science and its impact on various aspects of our world. To express our deep appreciation, we would request Dr. Archana Sharma, Dr. Janvi Falke, Ms. Monica Sagar to present each panelist with a token of gratitude as a symbol of our admiration for their contributions to this event. Let's once again give them a warm round of applause. We would like to welcome our first panelist, Ms. Neha Bhatnagar. Ms. Neha Bhatnagar, thank you, ma'am. We would also like to welcome and thank Ms. Sharmistha Mukherjee. Thank you, Ms. Sharmistha Mukherjee. We would also like to thank Mr. Rahul Agarwal for being with us here today. And finally, thank you to our alumni, Mr. Uday Soni. Thank you to all the panelists once again.
Let's now embark on an extraordinary journey to CMS at CERN. With our immersive virtual tour, we will witness firsthand the marvels of particle accelerators and detectors.
Our respected guest speaker, Dr. Archana Sharma, will take us on an exhilarating journey into the world of particle physics, the groundbreaking discoveries in the domain, and its relevance in the field of modern science. She will help us explore how the discoveries in the domain of particle physics have influenced our daily lives, driving technological innovations and progress. So, fasten your seatbelts as we undertake this extraordinary expedition into the very heart of particle physics.
Hello, everyone. Good morning. Zoltan, can you hear me? Hello? So those are my colleagues who are at the experiment, and they are going to walk you through, and we'll all go together for a virtual visit to where I have been working. Sound nahi aa raha na usme? So while they are connecting, can somebody tell
Yes, yes,
me?
we can hear you.
Oh, wonderful. Zoltan, hello, can you hear me?
We can hear you and see you both.
Brilliant, very good. So please, let's get started. All the students and teachers and visitors here are eagerly waiting to see our experiment. Let's get started. You see my colleagues there. There is Noemi is there. Of course, this is not a wonder for you all, children who have grown up in the internet age, but for us it is still a wonder that you are able to visit 7,500 kilometers away from where we are sitting. But let's go.
We are taking 2-3 minutes
Oh,
just
sure,
for
sure.
adjusting few things. But
Okay.
we are ready in principle, but just about 2-3 minutes. We are changing shoes and everything because we have to go into the cabin.
All right. That's Ashok, Dr. Ashok.
Yes.
Okay, so by the time they're changing shoes, because you know when you go down 100 meters, you need to have safety shoes. And they are those steel toe shoes so that you don't hit into, it's like a construction site. So you have to be extremely careful. And we are lucky we have actually Professor Ashok with us, who is from Delhi University, is there at the moment, who will also be part of the team that's taking us to this visit. So who will tell me, have you heard about the compact muon solenoid experiment? Yes? No? No worries at all. That's why we are here. Ah, one hand is there. Very good. Where is the hand? Oh. Okay, good, good. Very good. There, I see the hand now. So, what is a muon, you know? Why is it called compact? Do you know? We are going to look at all these questions. I hope my colleagues can wear their shoes very fast and quick, and we enter the cavern soon.
Yeah, we are getting ready.
Who's got the camera? Ashok? .400 people 400 plus people are waiting for you.
Okay, we are starting now.
Brilliant, brilliant. So are you sharing your screen or the camera?
Recording in progress.
Great. This looks like a good sign. Let's go ahead.
Hello, everybody.
Hello, is that Archie with you? Wonderful. So let me introduce my colleagues. So one of them, as I just said, is Professor Ashok from Delhi University. And the second...
Archana, your sound is very, very small for us.
Yeah.
Okay, no problem.
Now it's fine. Now it's fine. Yeah, now it's fine. We can hear you very well.
So the second person you see is Archana Sharma, okay? The lady over there. And we call her Archie just to differentiate between the two of us. So Archie and Ashok are going to take us through this beautiful experiment, one of the most beautiful experiments on the planet. So over to you, guys, let's go.
Thank you, Archana. So my name is Ashok Kumar, and I'm working for this experiment since last 2 decades. And today we are going to have a glimpse of the CMS experiment, both on the surface as well as in the cavern. So this in the cavern means in the tunnel we will have a visit, and we will show you important components of this detector. Archie, to you.
Okay, so I will assist you on the surface, and Ashok will go in the tunnel and...
Okay.
Okay, so Ashok will go in the downstairs and will show you about the detector. So, starting with the introduction of the CMS.
Okay, so as you know that we have a Large Hadron Collider as a biggest experiment on the Earth. We have a 27-kilometer tunnel. We will have a glimpse of this small part of the tunnel where CMS experiment is being situated. There are different components of the CMS experiment. Archana might have explained you something. If not, we will have a real glimpse of those parts of the CMS detector. What we do in this experiment, we are just colliding small particles like protons. So you might be knowing that protons are very small particles. Slides as well. Yes, we will share the some slides as well where you can see the real photos of this aerial view of the experiment. But the lines which you will see are actually inside the earth, roughly between 50 meter to 150 meter. The tunnel is situated below the surface of the earth. So this is the tunnel you can see, and there are different parts of there are different sections of this tunnel where these experiments has been situated. For example, CMS experiment where we are visiting today, there is Alice, there is Atlas, there is LACB, and behind LACB you can see the airport as well as very good view of the Lake Lemon. It is near to the Geneva city. So in the CMS experiment we have different parts, because when we collide protons and protons, when we collide protons and protons, it creates lot of energy. Lot of energy, according to Einstein's principle, is converted to mass, E is equal to mc square, and we try to discover these massive particles, because these massive particles decays immediately to different stable particles, for example, electrons, muons, hadrons, and so on. Maybe these terms are very new for you, but these are the terms which we are going to use very frequently in the experiment. This is the glimpse of the experiment. This is the, so you can see the height of the experiment is roughly 15 meter, the length of the detector is 22 meter, and there are other sections which are beyond this 22 meter. And you can see that if you have a cutout view of the experiment, you can see different parts inside it. But we are going to see is the overall view of this experiment. You will see these red parts, which is iron. You can see some interleaved detectors within this red parts, those will be muon detection chambers. And then you have the inner part where you have the calorimeter. Behind us, we have the big picture. And in the big picture, it is the real view of the, realistic picture of the experiment. So you can see the dimensions of this experiment, which is very, very large. So if you take a full picture, you cannot take in a single camera. But you can see, shortly we will show you the big picture where you will have the different parts of the detector. If you cut detector at the middle, at the barrel part, at the middle, you can see the different parts of the detector. What are the important features of this detector? You have a very, very strong solenoidal magnet, 3.8 Tesla. If you do MRI or something in the nearby hospital, the roughly magnetic field you face is roughly 2 Tesla or 2.5 Tesla. Here you have a 3.8 Tesla magnetic field. So this is very, very large magnetic field. Archana, you can speak in this.
So CMS stand for the compact.
You can come here, Archana.
So CMS stand for compact muon solenoid, and so solenoid is one of the biggest part of the CMS. And why we need such a big solenoid? Because as Ashok explained, we collide the particle in the LSE tunnel with at a very, very, very high energies. And when these particles produce the results of the collisions, we need a big solenoid for bending these particles. So in order to measure the momentum of these particles, so as big is the energy, as large is the magnetic field, the smaller is the bending, and vice versa. So the solenoid of this CMS is the biggest part. This is a superconducting solenoid, so a coil made up of fibers. It produces a magnetic field of around 3.8 Tesla, which is 100,000 times greater than the magnetic field of the Earth actually. And then you pass the electricity through this coil, which is very, very high, around 18,500 amperes, and it produces the magnetic field, a superconducting magnetic field without any resistance. So this is one of the biggest part of the CMS experiment. The total weight, as you can see, of the CMS is 14,000 tons, and the CMS magnet contributes in this weight around 12,000 tons. So you can now see that how big is this magnet. Most part of the CMS is situated inside this magnet. This is all the tracker part and the calorimeters, which measure the energy of the particles. They are inside they are fitted inside this magnetic coil, and in order to contain these magnetic field, there is a large shielding or this iron material that you can see in the red color, which is outside this coil, and here we have our also our muon detectors. So in the center of the detector, there is when the particle collides, so many secondary particles are produced. The aim of the CMS experiment is to photograph the results of these collisions. So it has to measure every particle and then trace back the track from where the collision starts. And this we do with the help of the different detectors. So the solenoid is used for the bending, then the inner part of the detector, which is made up of the sensor, the silicon sensor, which we call the tracker. It is used to measure the tracks of the particle, and then outside is the calorimeters, which measure energy of the particle, and then outside the muons, which are Yeah, so yes, you can see here in this picture. So the first part is the silicon tracker and silicon and pixel. There are two type of sensors. This is the closest to the beam pipe, or closest where the collision. So this is very sensitive and receives the most part of the radiations, the background and everything, and that's why this also needs a very careful inspection because of the aging, because of this large background. And then outside there are the calorimeters. So as I said, the calorimeters are used for measuring the energies. So we have two type of calorimeters. So the first is the electromagnetic calorimeters, which measure the energy which is deposited by the electrons and the photons. And then outside there are hadron calorimeters. So hadrons are the particles which are made up of quarks and gluons. For example, pions, kaons. So these particle deposits their energy in these hadron calorimeters. Also, the one of the other feature of the hadron calorimeter is to measure the particle which are undetectable. For example, the neutrinos. So this hadron calorimeter also measured these invisible particles because of using the difference of the energies deposited by the particle on both sides. So if on the one side the energy is bigger than the other part, so the difference of the energy they use to contribute, they are coming from these invisible particles. So yeah, so outside so as I said, these all these tracker, the electromagnetic and the hadron calorimeters, they are inside this superconducting solenoid, and outside we have the muon detector. So because muons are the particle which cannot be stopped very easily, they can travel through a long distance. So and these are also one of the main part of the CMS. That's why in the name of the CMS we have compact muon solenoid. So the muon detectors are situated inside this iron return yoke, which is used to contain the magnetic field which is produced by this superconducting solenoid. So for the muons we have actually we have now 4 kind of detectors which are used for detecting these muons. So in the barrel part we have the drift tube chambers, and then we have the RPCs, the resistive plate chambers, and in the end cap we have the CSCs, the cathode strip chambers, and then we have the GEM. These are the new detectors which the Archana ma'am is the main of our the motivation to bring this detector inside the CMS. And there is a lot of hard work, lot of R&D, and lot of work from all the contributors, and India is also one of the country who is responsible for this building this detector and taking part in the operations. I think we can.
Ashok is ready now. Thank you, Archie. Thank you
Oh.
so much for the introduction. Over to Ashok now. As you see, he is ready to go, and he is going to show us now and walk through some exhibition areas and then downstairs, correct? Thank you. Over
Yes,
to you.
exactly. So you can see these small, shiny components of this detector. These are made up of silicon. These are made up of silicon. So you can see a mirror-like a structure. These are silicon detectors. So as Archie was saying, that at the center of the detector we have silicon detectors. So these are the real silicon detectors which we are using. You can see the electronics associated to this. So as the particles, charge particles pass through this detector, they give you electrons and holes, as you know in semiconductor physics, and then the charge, the electrons are being collected here, and the signals are processed like in your mobile phones. You do the analog to digital conversion, and from digital conversion you go to the back end of the detector. So these are the real small detectors, and you can see the big
assembled detector of these small silicon detectors. You can see the big detector as well. So these are the in detectors being situated in the innermost part of the CMS detector. We have, we have to measure the momentum of the particle using these detectors. So these are very, very small. One layer is in micron actually, and thus there are strips actually. There are lines inside these detectors which you cannot see with your eyes. So the point is that you have to use care. I can show you the other this part. For example, here you can see these small detectors using this microscope, and you can see these small elements. Right now you can see the pixelated detector where you have a small pixels, and the electronics is being bombarded on this detector. So you can see small pixels using the microscope here, but with your normal eyes you cannot see these detectors. So these are the parts of the innermost CMS detector. Now we go to the other part of the exhibition. If you see, can they see the large muon detector here? So for example, here you have a big large detector, and now you can see the strips. Actually you can see the strips with your eyes, because we are in the outermost part of a detector. There you can see the strips of these detectors with your eyes, but in inner part you cannot see. As you go beyond, from inner to outer side, your radius increases, your volume increases. So this is the big detector which is used for the muon detection. These are the detectors which has been used to successfully detect the Higgs particle in 2012, and the Nobel Prize was given in 2013. So these are the real detectors which are being situated inside the CMS. Over to you, Archie.
So we, okay. So they are going now towards the lift, and there we will see that so the tunnel is underground at about 100-meter depth, and then Ashok will show you the different parts of the detector as much as we could see. How this CMS, this is a very huge detector. So the question comes, how it was built inside the cavern at 100 meters down. So the thing is that CMS is also depict a very amazing engineering. So the whole detector was not constructed in one go inside the cavern, but the detector is divided into 15 slices, and then 15 parts of the detectors, they were engineered on the surface. One of the reasons to do this was because this was it is easy to do this access, and then also from the security point of view, and all the services, they are easy to access on the surface. So they have built the detectors in 15 parts. Okay, so now you can see here the lift is coming up. So you can see the distance is decreasing. So the
please gather your questions. We will do a Q&A after. I will try to see how much you understood out of it, right? So we are going down, as you see, as Archie was explaining, and Ashok is inside the lift. When we were testing the magnet of CMS, this lift was tilting, It's such a strong magnet. It's in fact one of the strongest magnets on the planet.
Oh, okay. Okay, so now they are going down, and we are going to lose them. So yes, we continue here until they reach in the cavern. So yeah, let us know if you have any questions or anything you would like to ask.
Okay, questions. One quick question by the time the lift goes 100 meters down. Yes, you. Quickly. Okay. How do the detectors work? Yes. We will explain. I will explain in my talk. Please. This is a long answer, so.
All right. Thank you.
Quicker one. Anyone else who's curious?
Any other question? Yeah.
Why does it have to be so low underground?
Why, Archie, you want to answer? Why should it be so low underground?
You can go ahead, ma'am.
Okay, so first of all, Switzerland is a very tiny country. It's like Noida or Gurugram, and 8.5 million population. They don't have so much space on the surface. Number two, anything that you work with radiation, you want to build concrete structures for safety. If you go underground, half the work is done by nature. And then you can, of course, prepare your concrete walls, which are reinforced by iron and by borated concrete and borated perfluoroplastics. That we go underground so that there is absolutely zero risk of any radiation to the residents who live there. In addition, it really takes the minimum space. And we'll get more into the answer of this question because I see Ashok is ready in a new room which he is going to speak
Can I ask
about.
something?
Over to you, Ashok.
Ma'am, can I ask something?
Yeah, we are in the service cavern. We are in the service cavern. We have different racks. You can show, Naomi, you can show different racks where we have the services of the experiment as well as fibers for taking the data to the backend. So for example, here we are taking the data from the experiment using the optical fibers. Why we are using the optical fibers? Because electric signal is converted in the experiment to the light, because light can be, transmitted very fast. So they reach the in the computer data acquisition system very fast. So we are using a fiber readout here. You can see so many racks populated with the fibers here. I am showing just one part. There are many racks in this area, and we are roughly roughly 30 to 40 meter here. But then we will go to the other part of the experiment. It will be more deep, roughly 100-meter deep. But right now we are at the intermediate level where we have all the signals coming through the fibers, and you can see how these fibers are being erased, how the cooling of the racks has been done, and how this area has been excavated to populate the signal readouts of the different parts of the detector. Thank you.
Thank you, Ashok. So, 100 million mobile cameras are in this big room taking data. Imagine something like that. But taking data 40 million times a second. That's the challenge. And what you've seen is really the brains of CMS gathering all the information from the experiment, which is then taken upstairs to the control room, which we will visit later. Archie, Ashok?
So as Archana ma'am said, so there are 40 million collisions produced in 1 second, and you may be thinking that how we store such a huge amount of data. So we have a system at CERN which we called grid. So this is like, so we have different parts of this grid. We store the data on the different levels. So the first level is called the tier 0, which is at CERN. So the raw data, the unpolished data, the data that we got from this collisions, they are stored first in the tier 0. So this is called the raw data. And this gives us the first look about what we are getting in the collisions. Then there are tier 1 centers. So this raw data is then sent to the tier 1 center. So I think there are 7, if I am not wrong, tier 1 centers. France, Spain, Italy, Germany, and also one of them is Taiwan, then UK and US. So these are the tier 1 centers. So then this after making the copies of this data in the tier 0, the data is sent to the tier 1. And after that, from the tier 1 centers, there are again the tier 2 centers. So not all the data, but then we polish the data. We keep only those events which are useful for us, which are useful for the physics that we are interested in. And this data is sent to the tier 2 centers then. India is also one of the tier 2 centers in this Tata Institute, Mumbai. We also have a tier 2 center. So what is the good thing about is this grid system that any physicist, any scientist sitting anywhere in the world can use this data situated in the different parts of the world. So yeah, so this is one of the greatest, because the data that are produced at CERN is on of the order of petabytes. So it is not possible to store this data at one single location. So we have hundreds of thousands of computers that are used in these different grid centers, and they store the data, and then it can be used anywhere in the world.
Thank you, Archie. Did we lose Ashok? Can you figure out where is he?
No,
Meanwhile, question.
I think I am audible now. Okay.
Oh, very good. You are there. Sorry. Keep the questions. We'll come to them later. You can see Ashok has been doing there. He's walked into special keys and special locks. So Ashok, over to you.
Yes. I'm going into the experiment. Follow me. I am in the tunnel now.
Now you're in the tunnel, okay.
I'm going to open the experiment.
Yes, it is. You
going
guys
to
are
open
lucky.
the experiment.
You all are lucky that we are able to go in the experiment today. Otherwise, if LHC was running, which it was a few days ago, we were not able to go inside, because of the safety. But today, we are so glad to show you our beautiful experiment. And there we are. Oh. Look at this. Can you show the whole experiment? Yeah, this is wonderful.
Yes.
Yes.
This is experiment, full experiment. There is a beam coming here, but it is being shielded right now. You have the iron. You can see the iron here. You can see the experiment inside. It is a big. Now you can see the dimensions of the experiment as well. Right. This is a real experiment. You can see the cavern, full cavern here.
You can show a person on the cavern, so then they will realize the scale, if it's possible, Naomi. Can you show someone working
maybe on the surface
Not
they have the slide.
On the cavern floor. This is 6
but
solid
at least
building.
They can see this.
Yes. Yes. You can see the keys are bending because of the magnetic field on the fringes. So if you have a pacemaker, you have to be careful if you go there, right? In the beginning, we created these rules on how to behave. Look at these keys. And even your shoes, if you're not careful and you have magnetic sole, you will be pulled towards the magnet. So very good, Ashok. Thank you for showing us this magnetic field.
Yeah. Okay.
Ashok, gems bhi dikhana hai.
Yes. Okay. Now you see the different parts of the detector. In the side balconies, we have the powering stations, powering wires, like the nerves in our body. We have the powering wires, the services, the cooling, the gas for the experiment. It is going like this. So all these balconies are filled with these experimental, experiment services which we need to run the experiment. Let us go to the other part. Now I am on the X2 level. X3 level, I guess. Yeah, X3 level. So second floor. Let us move.
So it's a free gym when you do particle physics. You have to go up and down.
So this is the other part of the detector. You can see the other section because experiment is closed actually. Experiment is closed, so you can see the other side of the detector, the big side of the detector, okay?
Right.
So you cannot see inside the detector, inside the CMS because the detector is closed and taking the data actually. So, and magnetic field is on. So right now you can see different detectors. I don't know. They can see the behind the iron. They can see these RPCs. The detectors, the gases detectors. Okay. So like these detectors, the resistive plate chambers which are being installed just adjacent to this yoke, the iron yoke, you have the different parts. You can see on the bottom actually some cooling lines, the cooling circuits, the water circuits which are cooling the detector actually. And then you can see these blue cables which are powering cables. The copper cables are either gas cables or the water cooling cables. The small fibers you can also see which are signal readouts of the experiment. The red cables are very high powering voltage cables. Now, the important section you can see on the side, you have all these services are being connected to the balcony. There, these are being read out or they are being controlled. And there are different levels. We are on the second level. There is a ground, there is a rear level, there is a first floor, there is a second floor, and we can go up to fifth floor actually. There are 4 more floors in the experiment actually.
Naomi, sorry Ashok, can you show the shaft?
Yeah.
Can you show the shaft?
Shaft.
There, yeah. So if you look up, where are we?
Yeah.
So
Yeah.
that's the top of the cavern, and as you see, there is a lot of air conditioning or air that is needed because we are underground. We need to have several exchanges of fresh air. With the COVID pandemic, we know fresh air means a lot. So we need in this cavern constantly fresh air coming, and we are at an overpressure in the cavern simply because any dust particles or anything that can be contaminated can be recycled and then filtered out. So Ashok is now walking to the negative end or positive
I'm going
end?
to I'm going to a floor below.
Okay.
Or maybe I can show them the gem services and the control of the gem detector.
Okay, please show the control
Now you can
room.
see another view of the detector.
Yes. Are we going to the control room later?
We can go after the UXC visit.
Okay. So let's summarize here and go to the control room.
So this is one of our responsibility we are doing. So we have the gem here, and if you see inside the rack, we have the powering cables, the low voltage powering cables. We have the patch panel for the fibers. We have the low voltage cables, and we have the low voltage modules. The detector is on, so you can see the different channels are working fine. So this means the detector is switched on and everything is working fine. So this kind of system is needed to run the system by powering the different sections of the experiment. So this is one of the part where Archana and we are responsible to run the experiment. This is a gem experiment inside the gem detectors inside the CMS experiment. Okay, let us move to the other part. I don't know. So there are different racks.
So how do you control them? On the mobile phone, you have the touch screen and you manage to control everything. But here for the detector, you need to have all these cables, millions of them. You need to have a cable management team as well, which knows each cable is labeled, barcoded, and then there's a database.
We can go.
Yeah.
Okay. We are going one level. We also on the surface of the CMS we are going.
Okay. We will go now to the.
So we can show them we are going. So we can show them the experiment from bottom to top.
Yes. You're on the floor now.
So they can, we are on the floor and they can see the foot of the detector. They can see the, full detector from the surface.
Yeah. So
from
now you can show
floor
the
of
shaft.
the detector.
So you see this big well-like thing on the top. This is the 100 meters that goes to the surface. From where the experiment was lowered, like Archie was saying, bit by bit. There are 15 pieces. Actually, 17 in total. Archie is here and she's standing on a plug, by the way. Imagine moving the plug. This plug itself is 200 tons. So the heavy pieces were first brought on this plug, then lifted a little bit, just like a bucket of water. Remove the plug that would go under that big, poster that you see of CMS over there. This plug will move, and the object or one piece of this heavy object, the red thing you see on the left, will then be lowered just like a bucket inside the well. So it has been a very long engineering exercise from where the lowering was taking place. Archie.
Yes. So one of the main thing that give us the advantage of dividing the detector in these 5 slices, that whenever we have to do some intervention, which we call the shutdown periods, we can open the detector. So now the detector is closed. As we said that we were taking the data a few days back. Magnetic field is still on, and due to some problem in the LSC, now we are taking only the cosmics data. So whenever there is a shutdown period, there is a maintenance period, so we can open these detectors in the 15 slices, and then we can do the necessary interventions because these different parts of the detectors, they are very complicated. They required the regular maintenance. Okay, over to Ashok.
Yeah, so we are at the bottom of the detector. You can see the big, so as we were saying, different slices, you can see one full slice here. I don't know they have the light or not, but anyway, you can see these different wheels of the detector, different slices of the detector. We are under the experiment, so you can see, all the services going to the different parts of the detector,
We
and how
cannot
these
see.
services.
Ashok, we cannot see. Archie, we have 5 minutes to wrap up.
Okay.
Yeah, let Ashok show the full scale of the detector, which I think it is very impressive. So, Noemi, just show a full shot. See, each of these cables, each of these pipes is there measuring things at the level of
They can at least see
microns.
me and the dimension of the detector.
Yes, brilliant. Thank you, Ashok.
Now you can compare my size.
Yes, very good. Yeah, we can calculate your height and calibrate the detector. Very good.
So I am 5 feet 6. I am 5 feet 6 inch. So you can compare the full dimension of the experiment.
Very good. I think we will have to wrap up here, Ashok, because we are getting late on the agenda.
Yeah.
Because coming to the control room will take time. I will show a picture of the control room in my talk later on. Right? Anything?
Okay.
Any last
Thank
message? Any last message you want to add?
No, they were lucky that they were able to see the experiment, because normally it is not seeable, because the experiment was stopped for a few days for maintenance.
I know.
So all of us were lucky that we could see the experiment today.
I'm lucky also. I can still see CMS even if I'm in India. Archie, any last point?
Yes, so then we try to give you a brief introduction. It was not sufficient, but due to the lack of time. But yes, in your talk, I think they are going to learn a little bit more about how we take the data, how the shifts are operated, and so many other things. So yes, we are lucky to be a part of this huge collaborations, and yeah.
Okay, let's give Archie, Zoltan, Noemi, and Ashok a big hand. Thank you so much.
Where are my MCs? Just stay here. Stay here with me.
See that the hall is full. Yeah, there you go. Thank you very much. We can disconnect from the virtual visit.
Thank you.
Yeah,
thank you.
Thank you. Thank you. Bye.
Bye, Ashok. Bye, Archie.
Recording stopped.
Thank you, everyone. You did not get an opportunity to ask Dr. Falke questions, so I've requested her if she can take out 10 minutes to answer your questions. She's happy to. So over to Dr. Falke.
Thank you. I'm allowed to speak again, yet again. Yeah.
Students at back, May I have your attention, please? Okay, I saw many bubbling questions when Dr. Janvi Falke was speaking, and you are waiting for it. We are giving 10 minutes where you can ask any question to Dr. Janvi Falke. She will be going to you, she will hear you, she will answer you, and you will understand how science and humanity both go hands in hand. Thank you.
Thank you so much. So just before I reach you and let you ask me the question, I wanted to tell you a little bit about the history of CERN. CERN came into being because at the end of the Second World War, when the Americans were the first ones to use the atomic bomb at the end of the Second World War,
Stand in the center
and then they refused, the Allies refused to share nuclear knowledge with the rest of the world, right? And very soon what they found out by the end of the 40s was that in 1949, the Soviet Union tested their nuclear weapon. That was unexpected. This was not expected by the Allies, that the Soviet Union would be so advanced that they would test a nuclear weapon. So at that point, what they realized was that in order for knowledge, scientific knowledge to progress, they would need people, as Isidore Rabi, the physicist, said, we need people to talk to, so that we are not alone in our quest to find out more. And that is when, using what was called Marshall Plan money, the Americans funded the establishment of CERN, which was an international facility. So also see, the scale of science has sort of massively expanded at that time, right? Earlier, particle accelerators, like the one in my film, which if anyone wants to see, let me know, was in a single institution like this one. By the time CERN is established, you need several nations to come together, and you need their budgets, and you need a 2-kilometer radius, right? So science has changed completely. So this is a very good symbol of both, again, the politics coming together with the history, with the science, with the need for scientific compatriots, etc., etc. Okay, questions. Someone had their hand up. Several people. Okay, fine. I'll go one by one. Okay, please.
So, ma'am, I read about how Paul Dirac found a negative solution to E equals to mc square, and from there he hypothesized that antimatter might exist. And then 4 years later, Anderson actually observed antimatter tracks in a cloud chamber. So, if you could talk about how important maths and making a hypothesis is when discovering things in science.
Okay, so the thing is, there are limits to how much you can use a particular discovery to extrapolate to all kinds of discoveries, right? Like Dirac was a mathematically driven physicist. Not all physicists are, especially not all experimental physicists are, and Archana will probably back me up or not, depending on her mood now. Where is she? But you can, so some discoveries are experimentally driven, others are mathematically driven through models that are used to interpret data that is obtained from facilities like this, which are massive now and which were smaller before. So of course, mathematics has played a significantly strong role in the physical sciences, especially since the beginning of the 20th century. But that is not the only way. You can find your way in not just through theory or through mathematics, but you can also find your way in through experiment, right? So there is no formula, essentially. There is a method, there is a rigor, there is a commitment to fairness and thoroughness and robustness, but otherwise, it's serendipity, contingency, convergence. It's actually fun.
Thank you, ma'am.
Thanks.
Can I ask the full form of here?
Yeah.
Can I ask the full form of CERN?
Full form of CERN. European Council of whatever nuclear. See, I know the English one. The CERN has a French full form, which is why I'm hesitating, because my pronunciation is horrible, and some of you will know French. So it's Centre Research Nucléaire.
Okay, and what are MEANS, if regarding that?
What?
MEANS, the experiment we just saw.
That I think Archana will be able to explain more to you, because she does it. Remember, I'm the historian of science here.
Okay.
Yeah. Yes, you had a bunch of questions. Yes. Yep. After
yeah.
Yeah.
So my question was that most of us who is sitting here, we are mostly following the same curriculum like CBSE or ICSE. And our curriculums are usually very streamlined. So like if I want to study science, I'm not given much option to actually go into the field of history or go into the field of culture with it. So what is your solution for us as students over here to integrate science with all these different fields?
Yeah, very difficult question. But at the same time, I think the fact that you're asking that question means that you will make effort, right? So that to me is a good thing. Second is science gallery-like institutions, right? Like, so when I said this is one particular way to resolve that concern by creating a public space for science where science is made cultural, right? So that's one way to do it. And when someone asks me what would I consider success for science gallery, and I think for me the biggest, how should I put it, the biggest indicator of our success would be when people want to replicate what we are doing. So for example, if within the Shiv Nadar school establishment, you were to have research festival-like creatures happening, right? Like where you take an object of scientific inquiry. Now the next exhibition we have is called Carbon, or you pick up Psyche, which is what we did before, or you pick up blood, or you pick up whatever, right? Whatever. And then you get yourselves to speak to it as if you were looking at it through sociology, through history, through psychology, so you see what I mean? You don't look at science projects as science projects alone, or history projects as history projects alone, or politics projects as politics projects alone. That would start giving you the depth of approaching this, because it's at the end of the day, it's not about sort of just doing interdisciplinarity in that way, right? Like, so it's not, while that doesn't mean that's not enough, that doesn't mean that's not good, it's actually quite fabulous. But studying history, or for example, doing a math major with a philosophy minor is fabulous. But does that mean you're looking at mathematics philosophically, right? So it's about cultivating an approach. It's not only about studying different disciplines that you're now not allowed to study together, right? So can you approach biology through sociology, right? So do you look at, or is social ecology interesting to you, right? So it's about that, to use a lens that a discipline is in a way refusing, right? And you say, how dare you? I'm actually going to approach it in this.
Thank you.
Right? That would be so it's about approach. Yeah, who's next? Yeah, okay, go ahead.
You had earlier talked about how imperialism and other factors had affected research in the modern day. Could you elaborate more on that?
Yeah, so you see, when did the explorations in a way begin, right? When what one might say strong empires with strong armadas, right? Like basically naval units who were able to navigate and take their ships to different countries and find different things there. And among the different things they found there were not only different kinds of animals and birds and trees and fruits and flowers that they'd never seen before. They also saw, for example, in the first wave of imperialism, silver in quantities that hadn't been seen before. Silver became currency because the old world found it in the new world, right? And so, in a way, what I'm trying to say is that, I mean, it was the Chinese who gave to the world gunpowder, navigation, the compass, and paper, right? But it is the European imperial kingdoms that mobilize them towards the conquest of the world. And why is that? Early modern historians often propose, and this is a contentious discussion, there are several historians with different perspectives, but effectively what they're trying to tell us is that the coming together of the Roman Empire with Christianity meant that there were empires who were interested in political expansion, but they were also convinced that they were right and they knew better, right? So the impulse was from evangelism. And therefore, the need to go out and bring the world into your fold, into your ways of knowing, into your ways of doing, into your ways of seeing, right? And that is what led to processes of consolidating knowledge, consolidating power, consolidating commerce, right? This is a very caricature potted history approach, but it's not incorrect, yeah? And so When all of these things come together, then the capture and conquest for both commerce but also for religion feed into the making of large Spanish and Portuguese empires to begin with, followed by the Dutch and the French and the British, right? And research is embedded in this. So on YouTube, you'll find a lecture by one of my senior colleagues called Simon Schaffer, who teaches history of science at Cambridge. It's called Newton on the Ganges or Newton on the Ganga, where effectively what he's trying to tell us is that, I mean, this is fact, all those bubbly last benchers, fact for you. The third known foreign language translation of Newton's Principia was done in the kingdom of the Nawab of Awadh. Now this is something we do not know here. We call it Western science came to India. That's actually not true, because data was flowing from here, from rest of the world into Europe, but why was knowledge being consolidated as power in Europe? That is the equation where commerce, politics, imperialism, and religion come together, right? So it's a very potted history, and there are very, very good scholars who've written about it. So if you want, I can also later give you references to read. Yeah, but start with Newton on the Ganges, and then read, Simon Schaffer is the name of the scholar. Yeah, okay, yes.
My question is that what if we decode the universe, we are able to find how it's made, then what's the next step after that? If we are sure, we are certain that it's made this way, then what to do?
Then what to do after that? I think relax and enjoy. Okay. No, we are very far from that, right? Like, no, I do have a bad sense of humor, but once we figure things out, so it's one thing to figure out what is the design of, what we are made of, what the world is made of, better than what we know now. There's still that question. Remember, science started out as natural philosophy. And why was it natural philosophy? Because we were trying to figure out not only how this world is made, but why is it made at all, right? And that's probably the next frontier then, to figure out, okay, we are made in this way, what are we made for, right? Why are we there at all? I mean, it's a question that bothers many of us even now. Most of the times I just kind of put it to rest and go to sleep. But I think that probably, I don't know, I can't predict, but that would be the next frontier. Okay, who's next? Okay, go ahead.
Ma'am, I would like to start off my question with an example.
Yeah.
Ma'am, a few decades ago, Americans actually planned to make their own super collider. But ma'am, the Catholic Association of America declined and protested against it because, again, it is against God's law according to them. So ma'am, my simple question is science and religion always going to be locked in horns, always going to be fighting each other?
See, it wasn't always the case, right? Newton was a very good Catholic. He was a very good Catholic, right? So religion and science have not always been in conflict. They needn't always be in conflict. There are different ways of looking at the world, at how it is made, but also what it is made for. Why do we have religion? It's because we as human beings want to figure out why on earth are we on earth, right? Basically, what are we doing? So I think it provided for us, it's of course a man-made social organization, it has provided for us a sense of why we are here at all. And science wants to say, we'll tell you how we are here at all. And that will lead us to the answer of why we are here at all, right? Like intelligent design, for example. I mean, but again, historically, if you go back to, say, for example, Epicureanism amongst the Greeks, or Charavak in Sanskrit philosophy, where they say, don't try to look for an answer for this question. You're here and that is all there is to it. Enjoy life, leave when you have to, right? So it's not a question that's easily resolved, and that is exactly why the formation of disciplines is an easy way out, because it leaves behind metaphysics, it leaves behind natural philosophy, it leaves behind the very fundamental questions as to why we even wanted to know anything about the physical world around us at all, right? And so that's why I think the positioning of, or pitting of religion and science against each other is something that is often mobilized in different moments. So I would say, for example, to understand this better, it would make sense to begin by saying who uses that argument when and why. So why is a particular group of people opposing the establishment of XYZ, right? So if you begin to understand their arguments, you will often find that the opposition comes from very, very everyday, mundane reasons like control over land, control over resources, control or cultural authority over people, right? So I think that would be a good way to begin to understand why at what point in history certain arguments become important. Because otherwise, what we know today for sure is that science offers us the most reliable way of knowing things around us, right? It is uncertain, it is tenuous, it is incomplete, but it is the best we know. And we know that this is as of today, we do not know more than that. And therefore, what was the struggle of religion earlier on, or more than religion actually, what was the struggle of the church against science when this battle even began? It was over loss of cultural authority. It was over loss of political authority, right? Sorry? Exactly. So, you know, what happens when someone comes and says, guys, this is not how the world is? It means the church's authority to collect the vast amounts of revenue and have political control over people declines. And that is why it's a problem. It's not necessarily a problem of how should I put it, incommensurability or antagonism. So to understand why people fight, what are the arguments they use when they fight each other, that therein lies the source of understanding why these two might be pitted against each other. Okay? Okay?
Good morning, ma'am.
Hi.
Yes, my question is that what were the politicians' intentions when they first came to build the particle accelerator? What was going in their minds, and what did the scientists, how did they sell the idea of the particle accelerator? How did they convince governments to build something which is multi-billion, it's a multi-billion project?
Yeah.
So,
what was okay, so here's the thing. This is something I've also, like I said at the beginning, I haven't been back to school in 35 years. I've been teaching only university people. So I'll come from that place. Tell me if you think I need to explain myself more, okay? So here's the thing. Before the Second World War, in no country was there a Ministry of Science and Technology. After the Second World War, there is no country where there is no Ministry of Science and Technology. So with the use of the atomic bomb, how should I put it? Funding and conduct of research and reasons or purpose of state, which is defense, came together like never before, right? Some of this happened during the First World War also with the use of poison gases, right? But the bomb was a spectacular illustration of what happens when politics and science comes together, which meant after that, no government in the world was ready to let go of control over science, including its funding. It was also, but it's not necessarily only a political motivation. If you see the size of the Manhattan Project, right? It was not possible anymore for single governments also, or for that matter, universities where science research was conducted before, right? So if you look at the particle accelerator, in the 1930s, it was what I call, in the 1930s is what I call baby CERN, right? Like the 37-inch cyclotrons, the 47-inch cyclotrons, the 180-inch cyclotrons, and then 2 kilometers, right? So who can fund this? Who can fund this? It has to be governments, right? And so it also becomes impossible to do science without the state. And when is the state going to fund it? It also has to control it. And here's the thing, right? Anyone who can run a cyclotron or a nuclear reactor can build a bomb, right? These are called dual-use technologies. So of course, even knowledge around it has to be protected, and who will? But institutions that can protect this kind of knowledge, which is again the state, right? So this is how it all came together. And as I said, when the Soviets conducted their first test, it was clear to the Americans that they needed people to speed up research. They needed people to talk to, because you can conduct research in a vacuum, but if nobody else is verifying it or nobody else is doing it alongside you, you're talking to yourself, Your claim is not valid until somebody else has verified it, saying, actually, yes, the apple falls no matter where you go on the planet, right? So that was the reason. So the way I started out, science and politics came together. So the motivation was not political alone, right? It was political for some reasons, it was scientific for other reasons. The scientists needed people who were of the same pursuit or same conviction to talk to. The politicians needed to control this knowledge, so they needed to know who had it and who was doing what with it. And therefore, those two things converged. Well, many other things converged, but those two things definitely converged, and that's how they used Marshall Plan money to establish CERN. Thanks. Yes.
Since you were speaking about the integration of culture and science, I wanted to ask, what value does culture add to science?
Science is cultural. Human beings are cultural. The scientists have culture of their own. Institutions have culture, right? Like, how do we know this? When you go into a lab, Archana was telling us a story of Biba Chaudhary, right? Science is, we are told that we should believe that science is neutral, universal, fair, robust, except for the longest time in history, it was people who practiced science who told us that women had smaller brains. They actually don't. I mean, how should I put it? Less competent brains. We were told people of color were less intelligent. So we also have science, well, research questions in science that are informed by social and historical prejudices, which are enacted in the research in the lab itself, right? And therefore, when we say make science cultural, we also want to say that you recognize that it's cultural. And then of course you work towards doing, because that is the first step towards saying, can we do away with these biases, please? Because socially we've now already accepted that women can do, if they want to, things as well as somebody else, or that people of different races can do whatever they want wherever, right? This is just by way of two quick examples. So that's what I mean, right? Like you recognize the cultural aspects of science in order to address the cultural biases that are present in science. Yeah. Ma'am? Yes, go ahead. Not every scientist is discovering a new thing. Some of them do, yeah. Huh. Yes. Next.
Emerge, ma'am.
Yeah, so opposition is the first principle, right? Like it's not called opposing. So here's the thing, there are two different, our young colleague here wants to know, there's sometimes opposition to a new discovery or a new theory or a new claim, and how does one work with that, right? So one thing is that, so where is the opposition coming from? Like my answer to her question, where is that opposition coming from? Yes, whoever, where is the opposition coming from? Is it coming on grounds of, is it coming from valid grounds? Is your data not sufficient to support your claim? Is your worldview not matching with, people around you? So you need to understand what are the sources, what is the evidence that is used to question your claim. It's not necessarily opposition. So if those grounds are valid, you need to change your thing. Yeah. 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 Yes. 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 Yeah. What is a scientist supposed to do? See, we are human beings at the end of the day, right? We are human beings, and that's why history is important, to know that if you actually have enough reason to believe your claim is true, you should stand your ground, because in the end we found out he was correct, right? So that's one reason is that therefore history is important, but it also makes the same claim again, that at the end of the day, we are petty human beings, which is why when someone says, I mean, it's a joke, it's not true, so don't fault me on this logically at all. We say the hard sciences are the hard sciences, and then there are these soft sciences like political science and economics and whatnot, right? Because they don't have hard data. let's play on those words a little bit and make a joke of it, which is that I think human science is actually harder because human beings don't behave. They do not conform to anything. You study particles, you understand the particles, tomorrow you design an experiment, you know what's going to, you might confront surprises, but you're not going to be completely surprised in that, everything is going completely awry. Human beings do not conform to anything, right? And so in a sense, so that's the reason why understanding science socially, historically, culturally is important, because at the end of the day, human beings are going to behave like human beings. And we are fairly, Hobbes said one thing, you can say another thing, I will say another thing. We are fairly despicable for the most part.
Excuse me, ma'am. Ma'am, my question is like, ma'am, my name is Ridesh Kumar from Mount Olympus and I am from grade 11th.
Okay.
Ma'am, like my question is, many countries are trying to make artificial suns and 2 countries have been successful. So what could be the advantage and disadvantages of making the artificial sun, as well as what is the proportion?
Artificial?
What is the proportion of advantages and disadvantages of making an artificial sun?
Artificial sun?
Yes, ma'am.
Oh, I think you should ask that to Archana. Because what would be the scientific advantages or not advantages of it is not something I am going to know. I think Archana will know the content of science better. Yeah.
Ma'am.
Yeah, please.
Can I answer? It is said alternative sun, and obviously in ITER, France, it is getting built. But there, that is for energy requirement. So we are not at present thinking of replacing original sun, but this alternative sun. But we are going to harness, energy from fusion reactors, and that is at ITER. They are saying that it's the alternative sun. So that is the advantage. You will get energy without digging for coal and petroleum. There are 2 students standing since long. Can we just this side? Then we'll come back to you.
But
Over
fusion
to
is
you.
not
at
an
all.
established technology at all.
Yeah.
Ma'am, Shiv Nadar was established outside the Sun campus. So, what is the relation between the art and the science in it?
They are both, how should we put it? They are both products of creative minds, right? Like society. I'm deliberating his question. He's asking Shiva. Yeah. Yes, and therefore what is the relationship between art and science? Yes, exactly. So they are both products of creative brains, right? Like science is, so how should we put it? There's no formula that if you become a practicing scientist, you will reach a particular outcome. It's similar for art, right? You imagine the world, you inquire, you ask certain questions of the world, and you produce outcomes in the world based on those questions and that curiosity. And that curiosity is at the heart of both art and science, right? Because at the end of the day, it's a human being, right? And you often see this, right? Like we've forgotten it. You often see this. Good scientists are often good musicians. Good musicians are often very good at math, right? Good mathematicians are often very good, solve very well crosswords and quizzes and things like that. Good quizzes are often also very good historians. So you see, it's all a mix of things. We somehow separate them in order to understand them and then forget to put them back together. So I think allow yourself to think creatively.
Ma'am?
Yeah.
Why was Switzerland chosen for as the site for the mega project, and what are the upcoming future from this technology?
Oh, why was Switzerland chosen for CERN? I think Archana will also answer that, but I can tell you that Switzerland was neutral during the Second World War, right? And because it was a politically neutral country, if you placed it in the UK, then it would be in Allied territory or old Allied territory. If you placed it in Germany, of course, the Germans were a big problem. And so Switzerland was both willing to invest in it, but also willing to give land and willing to give resources, etc. But it was also a neutral country. So the key thing is it was neutral. So again, you see, politics plays a role in how science, might be rooted. Yeah. Yes.
Hi, ma'am. Thank you. So, ma'am, basically, I'll start with a small example. It is common knowledge that when Galileo proposed that Earth will not and is not the center of our solar system, he was publicly shunned by the Catholic Church.
Yeah.
Do you still feel that ideas like these, or even scientific researchers, should not present their ideas in the public? Because if we try to think about it in a certain way, it is a violation of our basic freedom. it's a violation of our ideas, like it's a restriction on whether we can think anew.
Yeah, okay, so what are you saying? You're
I'm
saying?
trying to ask that whether a scientist who feels like, let's say, A should be a certain property.
No, they don't feel it and they
No,
don't
they
say
have-
they
they
should
have
be.
some-
They have found out
They have
that.
found
yeah,
out.
yeah,
They have their own research behind it.
Yes.
And they feel it is good enough to be a part of some science journal.
Yeah.
But then he is publicly shunned.
Yeah.
Or he is said, no, this cannot be right.
Yeah.
So do you still feel that these people should be shunned like this, or an opinion should be taken by them and then thought about, like, yeah, this is possible, this can happen?
No, of course it has to be taken up. Of course it has to be taken up on its merit, right? And it's the colleagues will check and verify, and also see, these are also sometimes tentative formulations, right? Like, so if you look at there's a book by a philosopher of science called Paul Feyerabend, who was quite a maverick, who, it's called Against Method, who was able to show us that, for example, the lenses that Galileo used could not have showed him what he said he saw. But he had a model, he had an intuition, he had an inference, both, right? Like, it wasn't purely sort of feeling. He had an inference that this should be the case, right? So of course, I think everything should be entertained on its merit, examined for its claims, and if it turns out to be not the case, of course then it's discredited, and if it's discredited, it can be put aside. If someone finds new evidence to support it, it can be brought back in. I think that's the method, right? Like, that's the rigor behind any scientific claim. Yeah. Yeah.
Yeah, I have a question. So it seems as if every single scientific discovery we've made has only left us with more questions.
Yes.
For example, a long time ago, let's take this chair for example, right? A long time ago, we wanted to figure out what this chair was made up of. What was like the basic unit of everything, right? We came to an answer, atoms. But then later we realized that they're made up of subatomic particles.
Yeah.
We thought at that time, okay, nothing smaller than that. Then we found out about other subatomic particles like
No, we didn't say there's nothing smaller than that. We said this is the smallest we know as of now.
Yeah, as of now.
Yeah.
And then every single time we reach such a conclusion, we're only left with more questions. Do you
Yeah.
think that this dance is going to last forever, or will we someday reach some conclusive result?
I don't know. I don't know. It's like his question, right? I don't know. There is possibly a hypothetical end to it, but there's possibly not. I mean, given what we see, both in the experiments carried out at CERN and otherwise, and also the efforts to make the alternative sun, for example, which is, or attempts at fusion, for example, and all of these things there's so much to know that I don't know when we will stop either wanting to know or there'll be nothing left to know. I don't know.
Yeah.
I have no idea. Would be a great place to reach. Yeah, no, absolutely. I mean, that's the productive tension, right? Yeah. Yes. Wait.
Ma'am?
Yes.
My question is like fairly ethical. When a scientist...
What is fairly ethical? Is it ethical or is it not?
It's about ethics.
Okay.
So, when a scientist discovers something new,
Yeah.
are they obligated to share it with the world?
I don't know. It's up to them. But yes, if you ask me for my opinion, I think let me put it this way. As human society, we functioned on the assumption that knowledge is a public good and knowledge is meant for humanity, and that's why we pursue knowledge in the, in the pursuit of bettering the human condition, mental as well as, in the sense, not mental, intellectual as well as physical. And so, in a way, yes, we are also obliged to know, right? That's why the schooling system emerged. I mean, never mind the fact that the hospital, the military, the mental asylum and schools all came up at the same time. So you put the math, you do the math together. Prisons as well. Yeah.
My question was that how different would science be today in the absence of the world wars?
Of the?
World wars.
Oh, in the absence of the world wars. No, I mean, there was science before the world wars as well. We would probably, as I said, we would probably have had the atomic bomb slightly later. We would have probably had proximity fuses a little bit later. So, we would have had terminal ballistic missile technology come a little bit later. We would have probably gone to the moon a little bit later. So the wars definitely accelerated certain kinds of technologies, but we had sort of all of that knowledge, but also the technologies are based on things we already knew, right? It's the application that was accelerated because of the wars. So yes, so crises, wars and crises have a certain role in accelerating the taking of research into areas of governance and defense. But knowledge progresses no matter what, right? Like in different ways, at different pace, in different places, yeah.
It's a brilliant way to understand, and we are so happy that Dr. Palke is here. There are so many questions. I can see 5 hands that side, 3 that side. Can you please mail those questions now, darling? Because obviously, ma'am, I'm sorry, Dr. Janvi, Dr. Archana is going to take those questions, and her speech at CERN is going to start.
Thank you all for your
But
questions.
please do mail those questions, because we will forward all those to Dr. Janvi. And what a session. I saw pin drop silence. One was asking and Dr. Janvi was speaking. That is the essence of this whole conclave. So Dr. Archana will continue now, and she will take your questions. She will interact with you all now. Thank you. Yes.
Thank you, Dr. Falke, for answering the burning questions of our curious students. Now, I would like to once again invite Dr. Archana Sharma to the stage for her keynote session. She will take us on an exhilarating journey into the world of particle physics, the groundbreaking discoveries in the domain, and its relevance in the field of modern science.
Thank you. First thing I want to ask is, how many of you are tired? है ना? बहुत थक गए ना? है ना? Don't worry. I'm not going to start. Sorry, can I have a changer? Do we have a slide changer? Is it working? So what we'll do is, we'll make it a very interesting session by asking questions, right? All of us are in the mood of asking questions, as I understand, and let's try to do that. So certainly particle physics, such an esoteric subject, what are we going to, why should I care about it, right? Higgs boson, God particle, you all have heard about it, right? And now, why at all should you care about it? Should we? Why should we care about it? Let's try to investigate a little bit. So, looks like it won't move. Can you keep the laptop up here? Can you keep the laptop here? Then I can move it myself. So yes, of course, we have now these projects which are 30 years, 40 years, 50 years long, and you will be the ones leading the projects that are happening in the world. Like the one at CERN, you've seen some glimpses in the virtual visit, but we were not able to show you everything, obviously. What I'll try to do is to show you that scientific research, as we also discussed in the panel, is of course at the cutting edge of technology, because today's discovery is tomorrow's calibration, right? Somebody discovered gravity. Who was that somebody? Obviously, and we do all our satellite launches using the calibration from what he did. And for today's discoveries that we are looking at, for particle physics questions, there are so many questions that are open. Have you heard of antimatter? Everybody? Sabne suna hai, right? So imagine that my friend Vinita ji, she is made of antimatter. Vaise I'm suspecting that she is made of antimatter, the amount of energy she has. So think, if I'm going to, give a handshake to her, what should happen? If I'm made of matter and she's made of antimatter? Only energy, right? There will be only energy. You agree? You have a question? She wants to say something. Very good, yeah. Not only she, I would also disappear because matter and antimatter, both of us should disappear. But we are here, right? It means that all of us are made out of matter. Is it right? So how did this happen? And those are some of the secrets we want to look for. And for that, we need to make a very big accelerator that you have seen already. And for that, we also need cutting edge technologies. I don't want to go into too much detail on the technology because if you have a question, I'll come to that. And you've already heard about the social impact, right? You heard about the economic impact. You heard about the medical and health applications that are coming out from particle physics. And clearly, we heard about a company here already on the panel. Someone has a sustainability carbon reducing company, if I understood correctly. So making industrial engagement and businesses out of the science that comes out is also what we try to do at CERN. So what is the nature of our universe? We all wonder, every time we, since the time we were little children, we keep wondering what is the universe made of? And what is the nature? What is the most fundamental particle that we have? So this is what we want to answer at CERN. Imagine that all of us are together, rushing somewhere, because the solar system is revolving at 220 kilometers per second. ऐसा लगता है हमको कि हम ऐसे भाग रहे हैं? नहीं लगता ना? But imagine, because it's all relative, na? We are sitting on the earth, so we are stationary. Just like when we are moving in a car, we are stationary. So imagine that we are moving at this speed. So now there's something to think about. So that's unfortunately a man and another anti-man. I gave you the example of Vinita ji and myself, but those are my matter-antimatter people. And sorry, when they shake hands, they are supposed to disappear. They did not, obviously, because that's why we are here. So at CERN, we do fundamental research. And in this fundamental research, we are so many people who work in collaboration, right? And in this collaboration, we have seen the number of societal dividends that come out. So who knows where the WWW was invented? Only one person, 2 people, 3. Yes, थोड़े लोगों को तो पता है.
It was invented at the CERN only by one of the persons working there. His name was Tim Berners-Lee.
Brilliant. कौन बोल रहे हैं? ऐसे करो तो पता चल जाएगा मुझे. हाँ.
Prabdeep.
Okay.
Sun City School at 12th grade.
Okay, thank you. So WWW कैसे invent हुआ? That we need to share data. They are petabytes of data, we said, petabytes. First, you don't even comprehend how much is a petabyte, And now we are talking of exabytes of data in the future. So petabytes of data we need to share. And for that sharing, we have not only invented the WWW, because a 23-year-old Tim Berners-Lee said, let's try the HTTP. You know the full form of HTTP, right? Very good. So look up if you do not know about that. But he made the HTTP so that people could share data among each other sitting in India or sitting in the United States or sitting in Europe or in South Africa. And that led to a revolution, because today the whole world is so connected, and the impact that it has had on our lives and the way we get up in the morning and the first thing we want to see is something HTTP. Is it correct? Is it correct? All right. So, of course, the Large Hadron Collider looks at answers to questions like where the universe, how the universe began, where did we come from, antimatter, and of course that's possible with these kind of apparatus that I have been showing you from some time now. So questions are open. What is the origin of mass? Anybody knows? Yes. The Higgs field, brilliant. And what is the Higgs field? Anybody?
When matter which has mass, when it interacts with the Higgs field, I believe it warps it, and it's related to, I believe it releases sort of Higgs bosons, if I'm not wrong.
Okay, something similar happens. That's already very good. But imagine that this room is full even further. And it's not only a room, it's like a stadium, okay? Imagine that we are in a stadium and it's full to the point that there are students from many schools all over India in that stadium. And then it is announced that Vinita ma'am is going to come. So some people may know her, some people may not know her, right? So you wouldn't bother so much. But think of somebody like a star. Anybody wants to volunteer? Any Bollywood star who's famous and whom you all like? Bolo bhai.
They are saying Shah Rukh Khan.
Who?
This crowd, this girl, Shah Rukh Khan.
Shah Rukh Khan. How many people like Shah Rukh Khan? Everybody. Okay, Amitabh Bachchan. थोड़ा और पिछला generation में चले जाते हैं. It's okay? I see more hands. So let's imagine that in this stadium, you just get to know that Amitabh Bachchan is coming. Nobody has given you any information when he will come or where he will come, because the stadium is very big. He can come from any side, right? But only from the knowledge that he will come. There is a whisper going on. Is it correct? Everybody will say, oh, you know that Amitabh Bachchan is coming here. The Higgs is the star particle that we have in all the particles that we have. And when the Higgs is around, this is the way the other particles feel the field of what happens when a star is coming, right? And that's how it will not be easy for students who are on the other side of the stadium, and if suddenly Amitabh Bachchan appears on the opposite side, it will be very difficult for people to come from one side to the other, because everybody will block him. Am I right? Everybody will block him. Kisi ko selfie chahiye, kisi ko autograph chahiye, right? So it's the way as if a particle on that corner acquires mass, क्योंकि वो वहाँ तक पहुँच नहीं सकते. They become heavy, and it's a very bad analogy, but it gives you some idea on how this thing can work. So there are many questions that we need to answer in our universe, and particle physics deals with these questions. So let me work through thoda sa aage. Yeah. So why is this slide here? Imagine COVID happening without preparation, without the scientific infrastructure that we have. Imagine that we did not study quantum mechanics. We did not study, and we did not have the electron microscope, the scanning electron microscope. We would have not been able to have a picture of the coronavirus protein the way we got it immediately the moment it could be isolated. And then, of course, that opened the doorway for the vaccine as well. All the readiness that we had was due to the study that we did in the field of physics, biology, chemistry, and again, we said in the morning as well that these are not silos that we need to break, in fact, and work together. So the first 3D atomic map of the 2019 coronavirus was given by the cryo-electron microscope. And those of you who do not know about the cryo-electron microscope, I encourage you to read about it, because in our country, I think there is only one cryo-electron microscope in Bangalore, if I remember well, in IISc. Okay, so I hope that you realize that every single day, anything you do is connected with science, whether you are eating food on your table or traveling, or you have seen our ISRO Chandrayaan, or you have your games, mobile phones, etc. Now let's try to go further. So this I think everybody of you is beyond this stage where You all know what are quarks, and you know what is the atomic nucleus, obviously, which has hadrons like protons and neutrons, which is the reason why the large collider is called the Large Hadron Collider. Hadron is just another name for protons and neutrons and for particles that interact strongly, you know, very strongly. The name is Large Hadron, it's given hadrons. And this is a very simple equation, you know, it just takes 3 pages to write it, and that's how the model, the structure of matter is actually described. But, you know, it describes the 4 forces of nature, and of course that's what particle physics means. But don't get scared that if you have to do particle physics, you need to be able to derive this equation. There are specialists who will be doing that, but there are experimental physicists and applied physicists like me who work on the technology to be able to observe the predictions that are given out of these kind of equations and these kind of physics. So yes, we know that our world, our universe is about 14 billion years old, and we keep asking questions, and what are the questions that we can answer at the Large Hadron Collider is what is going to impact our life, your life, the world of millions of people, in fact, all over the world. So let me show you a little game. This is to show you the Large Hadron Collider. You recognize the little helicopters? Yes? They are made out of Lego. Let's imagine they are made out of Lego. And we collided them and they broke up. Are these fundamental units? What are they breaking up into? Pieces of Lego still stuck together. So they are not fundamental, correct? So what do we need to do? We need to increase the energy. Yeah, we need to increase the energy. So let's go further. First it has to. So we increase the energy. What happened? Okay, increase the energy, and now do we get the fundamental particles coming out? Do you see them? Are they coming out? Bad animation, but doesn't matter. You get the point, huh? So when you increase the energy, you get the little Lego pieces. Do you see them? Do you see them? So now we know that these are the fundamental particles when we increase the energy. And are we able to put back the helicopters once we know how they look like? We can make them from the fundamental particles. So that's the game that we play at CERN, looking for what happened at the Big Bang. Now how does this connect together? Let's try to imagine. We have understood how we build atoms by using, you know, quarks and these fundamental particles, because we understood after playing these games, you know, studying, breaking particles together with energy, increasing the energy, we understood that there is something called the standard model of matter, particle physics. Let's call it like that. And you know what are the fundamental building blocks, and from these building blocks, we were able to make our atoms. You all know how to make atoms, and they look like cute little atoms, right? So we are happy, we know how to make the electrons, but we still, do you think we know the whole story? We don't know the whole story. Who has heard about dark matter? Everybody. Oh la la, I'm scared now. Dark, huh? Dark matter. And why is it called dark matter? Anybody? Zor se bol do. Yeah, you can't find it, you don't know anything about it, and physicists are very clever. When they don't understand anything, then they call it dark, right? So dark matter, dark energy, we don't know, and that's the dream that at the Large Hadron Collider, we might just find dark matter. So let's try to increase the energy, shall we? Right? You all with me? Oh, what happened? Do you recognize what came out? And this was not what we put in there, right? So you all have heard about one equation that is called E is equal to mc square. Even people who are not doing science know about this equation, right? So the energy that we use for accelerating the protons in the Large Hadron Collider, of course, or the Legos that we said before, can be converted into mass. And if we give a huge amount of energy, we can convert and make particles that existed at the time of the Big Bang. Do you believe in dinosaurs? How many people believe in dinosaurs? किसने देखा है? किसी ने नहीं देखा? Why do you believe then? Very good, excellent, because you found fossils, you found signatures. Similarly, the particles that existed at the time of the Big Bang, we can recreate, right? These dinosaurs, they represent particles that were present at the time of the Big Bang but do not exist anymore. And that's the fun game we play at the Large Hadron Collider, and we create new particles. These are pictures taken from the experiment that you have seen just an hour ago. One of them actually, not all, but you see these blue pictures, they are from the CMS experiment. That's from the CMS experiment. How beautiful that picture is. It means that from a collision of one proton and another proton circulating in this Hadron Collider, when they collide with very high energy, so many particles come out. And how many of them do we know, and how many of them are the unknowns? That's the task of the physicist. And we, of course, know many of the particles that are coming out from the collision, right? You recognize many things over here, but there are so many things that you do not recognize. And those are the unknown particles, unsuspected particles that we are actually trying to find. This is not easy at all, isn't it? Is it easy? We need to be working together. We need those people who write those very long equations to tell us what is the model, which are the particles that we should look for. We need giant detectors like the one you saw. We need giant detectors that can take photographs of these collisions. आप लोग कितने फोटो ले सकते कैमरे से 1 सेकंड में? How many in 1 second? How many photos in 1 second? 10, maybe करके जो वो होता है उसका auto mode, है ना? But you cannot take 40 million photos in 1 second, can we? So the detectors take 40 million photos or record these kind of events that I showed you in 1 second, and we need then computer engineers who will then look at this data. They will store the data, analyze the data, share the data, collaboration worldwide. So we are 257 institutions from more than 60 countries that are working in my experiment, the one you saw. That's how the accelerator looks like inside. You need to be a marathon runner to actually go 27 kilometers inside. How many of you can run 5 kilometers? Good. 10? बड़े फिट हैं भाई यहाँ. 15? नीचे हो गए हाथ थोड़े से. 20? Awesome. 25? Whoa. Have you done it? Or you ऐसे ही बोल रहे हैं? You have done it 25 kilometers? कितना दिन लगा? This is 27 kilometers, and even on a bicycle, it takes a long time. But all right, this is the largest microscope on the planet. And it's an oxymoron, because you are looking for the smallest particle with the largest microscope, isn't it? Just imagine. So, when you want to measure something on a scale, you've done mathematics, you measure a line in geometry, right? So your scale should be very accurate so that you're able to measure millimeters. Am I right? Your scale has to be accurately graduated. If it is not, your measurement will be not correct. Now here we are looking for a particle or the signature of particles at the level of microns. in a detector that was meters high. You saw 25 meters, 15 meters. Each piece is 2,500 tons. You know, one Boeing aircraft is 280 tons. So imagine how many Boeings in one piece, and there are 15 to 17 pieces there. So measuring it becomes an art, and that's called radiation detection. And one of the kind of detectors that are used in the experiment is my field, where I work. These experiments are underground. We already visited, so I can skip this. And you've already seen the beautiful CMS experiment. That's the computer center at CERN. And in 15 minutes, data is distributed all over the world when it's created. So one day I got a call from the press office. They said, Ashana, do you know this boy from Kerala? He's got the science prize from the chief minister of Kerala. So I said, I was a bit perplexed because normally I know pretty much all the high energy physics that's going on here, and I know all the physicists as well. But this little boy I didn't know. He was studying in high school. He looked at the open access data and he volunteered his computers for working on open access. It was very impressive, and I was, just to say that little kids, you know, they come up with novel ideas. So here I think you already saw this picture, so I won't go into it too much, except to highlight that those are the Alp Mountains, the airport. My house is close by over there, and CERN is this 27 kilometers underground that we already visited, and it straddles two countries. You see a dotted line, on the right side is France and on the left is Switzerland. So these we have already seen. These are more pictures of the experiment you visited. More pictures, more pictures. Imagine lowering this 2,500 tons piece, this whole piece, from 100 meters above to the cavern floor. BBC was covering it live. It was such a scare because 10 meters in 1 hour was the speed. So the 100 meters could take us 10 or more hours. And have you ever taken a bucket of water? You may not have done that, but you can imagine a bucket of water inside a well, and then you are pulling it up. Huh? It's going to swing, correct? And this is 2,500 tons. So our engineers had to really work overtime to make sure that the swing is less than 1 centimeter on either side. So there has been so many engineering challenges. So particle physics is not only about the physics, it's also a very big engineering challenge. So that's me downstairs in the cavern, and this piece here that you see, this piece here, and this detector that is being installed here is the gem detector that we spoke about earlier, and that's what has been one of my big achievements in my own life, where I conceived this detector and then created a collaboration which then built them and installed them over the last 10 years. Thank you. Thank you. And you can also see something else in my team. This is part of the team, obviously. The team is much bigger. That's Zoltan, who hid himself from the camera a little while ago. And that's Noemi, whom you also saw a little on the left here. That's Noemi. And how many girls do you see here? Isn't it impressive? Lots and lots of girls are there in my collaboration, 50%. Okay, so how do we do it? We must collaborate, and that's what I want to give you as a message, that without collaboration, nothing is possible. Collaboration is the new competition. We need to work, collaborate, and we are able to leverage the collective knowledge, which goes way beyond an individual's knowledge, to be able to achieve such impossible dreams and crazy dreams. Okay, so I will skip these things. I want to go straight to this slide where on Thursday, 8th of October 2013, the Nobel Prize for physics was announced, and it was given to Peter Higgs and to Francois Englert. Impressive, as you can imagine, thousands of physicists working over 3 decades, 4 decades, they found the Higgs boson. With all the challenges that I have not really enumerated, but you can imagine by now. That's our Director General, and somewhere in the crowd I must be hiding as well, but we were elated that the Nobel Prize was given because of our work. But the message I want to give you is that everyone is important, and I would like to felicitate my collaborators in India who have also worked on this experiment for the last 20 years and more, who have also participated and worked on analysis or building the hardware, building the detector. And we should be proud that we are there right in front. We may not acknowledge it, we may not be singing praises, but we do need to acknowledge that large experiments have a component of great pride when there are achievements that come out, right? So World Wide Web, I think we already mentioned, I can skip it. This also let me skip. I just want to mention now a little bit about the medical applications, since we did speak about that. So accelerators have huge amount of energy, and we can tune the energy. So imagine, we spoke about cancer as well. So imagine that we shoot this energy onto a tumor. You have all heard about radiotherapy, right? Radiation therapy. Because cancer is treated in many different forms, chemotherapy, immunotherapy, and then there is surgery. So there is another therapy where accelerators are used, and that's called particle therapy, proton therapy, or hadron therapy. Has anybody heard about it? Very good. Excellent. I'm so happy to hear, to see. So protons, they have a property that you can, just like a cricket ball, you know, you give the energy and it goes straight on the bat. It will only go on the bat. It's not losing energy on the way. But if you use normal radiation like photons, photons will go there like a torch. You shine the light, and the light that reaches over there is much diffused, isn't it? So energy is lost on the way when you radiate by photons, but with protons, energy is given to the target only. So the tumor is are the only cells, tumor cells are the only cells where energy is deposited and you kill the tumor and not the healthy tissues neighboring the tumor. So those treatments exist in the world, again, not in India, but rest of the world, and that's another of my dream, to bring these kind of technologies here. Okay, I don't want to go too much here. Let me just take a look quickly, how much do I have? Okay, let me just go further directly to this slide, where I want to come back to the point when I was sitting like you all young students, confused, unsure about myself, what to do, so disoriented. Every time a speaker would speak about a subject, I would be so enchanted that that's what I want to study. Today I listen to Dr. Falke and say, I wish I had studied history of science. It happens. If you listen to an archaeologist who has achieved something, I want to do archaeology. So it's a very confusing time in life when you're a kid, and serendipity plays a big role. So your job is to expose yourself as much as possible to the fields that interest you, and eventually you'll find your calling, just like Dr. Falke did. These are the students with whom I work, not only these, but some of the students. Maybe you recognize some people from Shiv Nadar school, some more down there. These are more students, so I keep spreading the STEM message. I wanted to highlight here, again, can you recognize somewhere is Vinita ma'am here somewhere? This is in 2019. We did a teachers training program with the Shiv Nadar schools, and this was an amazing result that we got, where we had 82 teachers coming from all over the country, and we spread the particle physics message, of course, but also the STEM message and how we can impact society with what we are doing in terms of mega science projects. Of course, by now you know that I'm really passionate about empowering women, and in my own project I have women not only from India but from all over the world who work together with me. Okay, so particle physicist can do everything. If you can do physics, it's not an if, it's just that if you choose physics, you can do everything. And particle physicist domain is one of the most sought after domains. 70%, 80% of the PhD students from particle physics go to banking. They go to finance institutions. They go into risk analysis and so on. So just to highlight that while we are building our detectors and taking data and gloating over the fact that there was a Nobel discovery as well, people are learning skills that are not learnt anywhere else. Big data, I don't have to convince you. Machine learning, artificial intelligence, financial management, mechanical engineering, space sciences, astrophysics, medical applications, industrial applications, and so on, apart from the big project management itself that comes around after you have worked for a long time in the field. So what we do really connects with the sustained development goals, and I would have to do another lecture if I were to go into each one of these in detail. So I just would like to end. I hope this is working now. It will come eventually. So there are several books that I have been writing along with co-authors too, highlighting the contribution of Indian scientific potential. One of them is for free. It's called Nobel Dreams of India. And another one is called India's Science Geniuses that maybe Vinita ma'am is going to speak about. Thank you for your attention. चलिए questions लेते हैं अभी. Yeah, ठीक था? आप दूसरा ले लो. Okay, now questions, and I'll come to you rather than you coming to me. One by one.
Yeah, so in your presentation you talked about dark matter and antimatter. Could you
ऐसे करके बोलो, Lady Gaga.
Could you explain the relationship between dark matter and antimatter, and what is it that is connecting both
It's
of
a
them?
long answer. One-on-one दे दूंगी.
Okay, ma'am. Thank you.
उनको दे दीजिए. Yeah, I'm sorry.
Yes, ma'am. I was reading on CERN's website about the gravitron. So it talked about how after the discovery of the Higgs boson, they're going to try to detect the gravitron. So could you just explain a little bit more?
You know, we need a huge amount of energy already to get to the Higgs boson. And we were surprised that it was rather light compared to what we were expecting. And the LHC cost about 1.2, only our experiment costs $1.2 billion. The second experiment cost the same. We have the LHC itself that costs, I will not say the numbers, otherwise I will be killed. But we need to balance out the resources with the physics that we can do. You know, and science takes its own time to develop. You know, the World Wide Web was just, the algorithm of the HTTP was made and put out there in the public, and see what happened to it. Today, you know, having internet is a human right. Okay, one by one. Yes, you and then you.
What actually are muons?
I'm sorry?
What are actually muons?
Muons? Muon is a cousin of the electron, and it is formed in decays of heavier particles. Muon is 200 times heavier than the electron, and it is a very useful particle in experiments because it can go through matter without losing energy. And you saw this very huge CMS detector, and then you saw this red iron. So the muon can go all the way. So imagine if the Higgs is decaying into 2 muons here, and for energy conservation 2 muons on the other side. So 4 muons becomes a gold-plated decay of the Higgs to be observed in the CMS experiment, and it was observed. एक भी ये बच्चा भी बोल रहा था, sorry.
I wanted to ask that I was doing some reading about the possibility of the Large Hadron Collider actually forming a quantum black hole. I wanted to ask how realistic is that theoretically, and if it is, how much of a threat could it pose to mankind?
Okay, imagine, do you know about cosmic rays? Little bit, right? Cosmic rays come from the outer atmosphere and they come and shower on us all the time. Right now, you have thousands of particles going through your body, many of them going in the other direction also because they are coming from the bottom of the earth. Some of them have energies which are way higher than what we use in the Large Hadron Collider, up to 100 TeV. These are called very high energy cosmic rays. And we are still here. Does it answer your question? Okay, thank you.
Ma'am?
Let's start from here. Yes.
In the Large Hadron Collider experiments, how are the protons isolated from the atoms to be fired?
What is, do you know what is hydrogen? क्या है बताइए nucleus hydrogen का? Now you got the answer? You had the answer. Okay. Anyone else? Yeah.
Ma'am? Ma'am?
ये वाला side खत्म हो गया वैसे, we were on the other side, but okay, go ahead.
Ma'am, so many people are saying that physics is in a slump now. Since the Higgs boson, no big discoveries have been made. What would you say is the way forward for science, and would you agree?
So, you know, when you have a newborn baby, do you say that life is finished now that the baby is born? So Higgs boson has just been born. We want to study the features, characteristics, decay modes. We might strike lucky. Higgs boson, we struck lucky that in the second year of running we found the Higgs boson. It could have been that we were running for 10 years and we could not have found the Higgs boson, but we were lucky. Now we are producing millions of Higgs bosons per year. So if we were to find some part, and we have already found 63 new particles, 63 new particles. We do not flash it as much as we should, perhaps, for you to know that nothing is happening in the field, but there are discoveries happening every single day.
Okay. May I request all school who are leaving because of bus, please take lunch. The student escorts from Shiv Nadar school, please go with them. They should have their lunch. Result will be announced in another 5 minutes. If your school is winning, obviously we will send the certificate to you. That is our promise. Please take lunch and go. We are here for another 5 minutes for question answers. After that, all questions will be mailed to us and which will go to Dr. Anshita ji.
Okay, aap bolo.
And can you leave without making noise because children are still interacting.
Ma'am, so is it possible that Planck's quantum assumption is wrong? And if it is, then what does that imply for physics?
Very complex question. बाद में इसका answer दूंगी one-on-one. Somebody here, yes.
Ma'am, what is the difference between particle
Okay,
accelerator?
children, can you please wait? We will announce result first. The schools which are coming from Gurugram, Noida, just wait for 2 minutes. Sameer sir, while Dr. Archana is answering that question, can you please announce the result?
I think we can, let's look at this, what's going on.
Let us give a warm round of applause for Dr. Archana Sharma. We are immensely grateful for for her contributions to the world of particle physics and for sharing her knowledge with us today. Thank you once again.
Ladies and gentlemen, it's time for the moment we've all been waiting for, the winners of the Rangdas team competition. Prepare to be amazed as these brilliant young minds showcase their innovative and artistic talents. We will start with the verbal mention to Sun City School for their theme, India's Scientific Strength.
Monica ma'am and Dr. Archana on the stage. And Monica ma'am, Dr. Archana and Dr. Janvi on the stage.
We would also like to invite Ms. Monica Sagar and Dr. Chana Sharma and Dr. Janvi Falke to the stage to facilitate the awards.
Sun City School is there or they left? So who is going to take award? Please go on stage.
Congratulations for your
Also, just after prize distribution for 30 seconds, we are going to announce a very interesting quiz round which will be open across India. So just listen to that and we'll send the invite so you all can appear in that quiz and win a lot of prizes. Thank you.
In third place, we have Salvan Public School, Asa Sharma, Asma Jain, Varnika Jain with their theme, The Amalgamation. Salvan Public School, if you could come up on the stage. A huge round of applause for our winners, please. In second place, we have Aravali International School, Drishti, Tapasya, Karthik, Ananya, Shagun, and Hareen with their theme, The Universe and Us Connecting the Threads. Congratulations, Aravali International School. Sector 43. A huge round of applause for our winners. And finally, in first place, we have Satya School, Nandika Ghosh, Zaira Kadri, Ananya Goyal with their theme, Cosmic Microwave Radiation Used in Sustainable Industry. Congratulations.
Children, you are requested to be seated for another 1 minute, please, till the children are getting prize. And the schools who have come from different part of Gurugram and Noida and Delhi, just stay for 1 minute, please, before you leave. before you leave, all those who are leaving, and obviously we will be sending this invite, look at this book, turn around and look straight this book. We are very soon going to have a quiz on this book, and you will be shared the invite, and the winner will get chance to interact more with Dr. Archana, and obviously will request Dr. Janvi also, and you will be getting prizes. All questions will come from this book only, which you can get anywhere in bookstore or Amazon. We will share invite with you. Thank you.
To conclude this remarkable event, we extend our gratitude to all the participants, speakers, and organizers who made this day possible. We would like to extend our heartfelt appreciation to each and every one of you for gracing us with your